Right. So, good evening to all. So, I hope everyone is present. Please raise the hands if you can hear my voice, screen movement, and other things are like doing well as of now. Fine. So, today, as I told you, that it is a very, very important session. So, we are going to see the working principle. See, one kind request to all. So, during that question and answer session after the class, please try to ask the questions. Yeah, heart of the induction machine. Try to ask the questions from the topics which we are going to cover today or which already we have covered in the previous classes. The thing is, if you're trying to ask something which I'm supposed to be discussed in the coming days, so for that I have to tell a big story. So that will kill the time. So my humble request, my kind request to all the students, please see that you try to ask the questions from the topics which we already completed and which I'm going to complete today. I hope this point is clear, right? Please confirm me. All of you raise the hands if you are clear with this, please. Right. Thank you. Now let me start with the working principle. See, in this working principle, we are going to see the complete working of a three-phase induction motor from the basics to the advanced concept we are going to discuss. And in this, I'm trying to make use of all the contents, all the concepts, all the laws which already we have learned in the previous session. So after this working principle is over, one should be able to answer to this following question. On what principle this so-called as induction motor rotate? The mechanism of conversion of power from electrical to mechanical, the role of the back EMF, then the relative speed concepts. And finally, I told you that for the production of torque, the relative speed between the two magnetic fields has to be zero. So that concept we have seen, particularly in case of a DC motor, that the field poles and the armature poles are stationary with respect to each other, and the relative speed between those two fields will be always zero, and there exists a continuous attraction and repulsion, due to which there is a continuous rotation. So coming to this induction motor, when I'm talking about the concept of pole formation, we have seen some basics of how the rotor of an induction motor rotates. So if I'm correct, I have used one terminology called as the rotor chases. When I'm using the terminology rotor chases, it is something like the rotor will rotate in the same direction as the field. So with respect to that magnetic poles, we are able to see the rotor is trying to rotate in the same direction. Now with respect to this complete working principle, we are going to see what are the laws, what are the rules which are available to know the direction of the rotor. So the complete thing we are going to discuss here, right? Let me start. The complete working principle of a three-phase induction motor, right? Please. See, if you are having any doubts, please try to write it on a paper, right? So at the end, you can ask me, but if I'm correct, I'll not give that scope for you to have the doubts, right? I'll do my best. So without doubts, we are trying to see the working principle. Done. Now I'll consider a stator here. So the working principle of a induction motor. Oh, working principle. Working principle. Right. So if you remember, basing on the rotor construction, we have seen two types of induction motors. One is the cage rotor, which is widely used. The other one is a wound rotor, which is rarely used when the starting torque requirement is very high. So it is a particular motor which we use when the starting torque requirement is high, or when we are going to start the motor with heavy loads. So if you want to start the motor with heavy loads, that is possible only by adding some external resistance in the rotor circuit, which is possible only in case of a slip ring, right? We have seen the classification. So the working principle of both these motors is more or less same, but there is some slight difference. What is the slight difference means? In case of a cage rotor, the rotor doesn't carry any windings, it have only the bars. But whereas in case of the slip ring, the rotor carries the windings, and those conductors are being wound in the slots of a rotor. But even though the cage of a squirrel cage rotor doesn't carry any windings, as it have only bars, there is some mathematical formula to imagine how many phases or how many windings are there. So here, if I use one terminology, so the stator flux lines are cutting the rotor windings, the rotor conductors, and EMF is induced. That will be a valid statement in case of a slip ring. Why? Because in case of a slip ring, the rotor have windings. But in case of a squirrel cage, the rotor doesn't have any windings, but we have to imagine that the rotor have windings. Already I told you the formula, and in that an EMF is induced, right? It is only the imagination in case of cage rotor, whereas in case of slip ring, we can see winding, and in that EMF we can see. So this is the difference. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. Done. Now what I'll try to do now means I'll try to explain the working principle. See, it is not like in your college levels, whatever the time your teacher might have spent, some 10-15 minutes, I'm going to spend the same time here. No, roughly, I may take some 2 to 2.5 hours, even more than that also, right? We'll see the thing best. It is not like on the basis of time I tell the working principle. So I pre-assume that out of my experience, it will take roughly that much time. We'll see. So I'll be taking a three-phase winding. Three-phase winding. Why? Because we are talking about a so so once again confirm me everything is clear. Audio, video. Someone has raised the hand. Right, done. So I'm considering a stator first, and in the stator I'll be considering a three-phase winding. So when you remember, if you remember when I was talking about a three-phase winding, please, those three-phase windings are physically placed with a space angle of 120 degrees. The number of turns per phase are same. Let N1 be the number of turns. And you know that these windings are distributed and concentrated. For that, I need to represent a winding factor. What is that winding factor means? It is a product of distribution factor and pitch factor. We have seen that. So when the windings are distributed, there is some reduction in voltage that is accounted with a distribution factor. And when the windings are short pitch, there is some reduction in the voltage which is accounted with a pitch factor. And the product, we call it as a winding factor. So let the winding factor of the stator windings be Kw1. So here I am using suffix 1 for the stator side, whereas suffix 2 for the rotor side. Rotor side. So it is N1 Kw1, N1 Kw1. Let the poles per phase be P. Let us take that P to be 4. Let us take P to be 4. Let the terminals be A dash, B, B dash, C, C dash, right? So you know that these three-phase windings are physically placed with a space angle of how many degrees, Baba? 120 degrees, right? You know all these things. So just these are the three-phase windings. I'm joining here A dash with a B dash and B dash with a C dash. I mean to say that the windings are connected in star. Similarly, if I'm taking a slip ring rotor, even in case of slip ring rotor, we have three-phase windings, and the three-phase windings, when even if I talk about three-phase windings, those three-phase windings are physically placed in case of rotor also. Please, I told you that in case of slip ring rotor, so it is not compulsory that the number of phases on the rotor the number of phases on the stator should be same. They can be different, but minimum number of phases should be 2. Why? Because the torque is due to the interaction of the fields or the poles. That is, there should be a continuous attraction and repulsion between the poles. As the stator poles are rotating, the rotor poles also should rotate so that the relative speed between the two fields should be 0. If the rotor pole should also rotate, means with how many minimum phases we can produce the rotating poles or rotating field means 2. So that is the reason the rotor phases should be more than 1. Minimum should be 2. So this is what I told you yesterday. The fourth point under the cage rotor, I told you the same thing. The operation of an induction motor is not possible with unequal poles. Why? Because poles are unequal, those attractive and repulsive forces are unequal, and hence the rotor may not rotate. But the motor can rotate even if the phases are unequal, but minimum phases on the rotor should be 1, that is greater than 1. Greater than 1, minimum should be 2. I hope this point is clear. Confirm me, all of you, raise the hands. Right. Now let us consider the number of turns in the rotor be N2 and the winding factor be Kw2. And you know that in case of rotor, the circuit is closed. So in case of slip ring, after that external resistance, the circuit is closed. But whereas in case of squirrel cage, using that end rings, the rotor circuit is closed. Unless and until the rotor circuit is closed, there is no concept of motoring. Why? Because for the production of torque, two magnetic fields are required, and the second magnetic field is due to the rotor current, and this rotor current is due to the induced EMF. The induced EMF can circulate the current only when the rotor have a closed path. Rotor have the closed path. So for that, maybe a cage rotor or maybe a slip ring rotor, the rotor circuit should be always closed. Without close, there is no concept of current. There is no concept of torque. The rotor cannot rotate. I hope this point is clear. Confirm me once. Confirm me once. Yes, done. So this is the stator, right? As of now, the stator is stationary. The rotor is sleeping. The fellow is in deep sleep. Which fellow is in deep sleep? The rotor is in deep sleep. I hope this point is clear. Now I need to make the rotor. Are you please wake up? Wake up. You are supposed to rotate. You have to rotate. I have to make the rotor to rotate. So for that, what I need to do means I have to take a three-phase current. So whenever I'm talking about a three-phase balanced currents, you know what is the meaning of balance. So those currents are purely sinusoidal or cosinusoidal. The peak value should be same, the frequency should be same, the time angle between them should be 120 degrees. So unless and until I specified, we discuss the operation only with balanced supply or whatever the conditions I have laid out. Why? Because at the end, when I'm talking about some miscellaneous concepts, I tell if the supply is unbalanced, how the performance will be. So that is a separate topic for some half an hour. But as of now, the regular class till the last will be a balanced supply. So unless and until I talk, whatever the three-phase current we are talking about should satisfy all those conditions. The current should be purely sine. The peak value should be same. The frequency should be same. The time angle should be 120 degrees. I hope this point is clear. Confirm once again. Confirm once again. Right. So I'm taking three-phase currents. Let those three-phase currents be IA, IB, and IC. Those three-phase currents be IA, IB, IC. So I'm giving a three-phase supply here. I'm talking only, this is the three-phase supply V. Like that, to every phase I'm giving V. V. So here a current is flowing IA. So reverse I'm drawing, just wait. So a current is flowing IA because of the three-phase supply IB and IC. IC. Then you know that whenever we pass a three-phase currents into three-phase winding, then we'll be having three individual MMFs. One will be along A axis, other will be along B axis, other will be C axis, which are oscillating along this individual axis. But the resultant of all those three individual MMFs is a rotating MMF. So because of these three-phase currents, and the three-phase winding, then we can see the resultant MMF is a rotating MMF. And what is the formula we are having for that resultant MMF? So resultant MMF is 3 by 2 times of Fm cos theta minus omega t. So I think in my starting classes, I told you to remember that whenever you come across cos theta minus omega t, it is a rotating one. Why? Because with the time, omega t is changing. With omega t, theta is also changing linearly. So if omega t is becoming 1, so theta is also becoming 1, then the resultant is moving by 1 degree. When omega t is becoming 2, theta is also becoming 2, the resultant MMF is moving by 2 degrees. Like that, with omega t, theta changes, and with both omega t and theta, the field or MMF will be rotating in nature. I think this was already explained in the previous classes. So cos theta minus omega t represent which nature? Rotating nature. As I'm having a rotating MMF, then this rotating MMF will produce as a rotating field, and I name that field as phi1, and I give a tagline to that: stator rotating magnetic field, or in simple, stator field. So what are the properties of the stator rotating magnetic field? It will have an amplitude of 3 by 2 times of phi m. Sir, what is the relationship between MMF and flux? It is something like this. If E is the EMF and R is the resistance of the path, I is the current flowing through that path. Similarly, if this is the resultant MMF and reluctance of the path is that one, then this is the flux. So MMF by reluctance of the path will produce as flux. So it is something like E by R is the current flowing through the circuit. MMF by reluctance is the flux that is passing through the circuit. So what is the magnitude of flux that is passing through the circuit is 3 by 2 times of phi m, where phi m is the peak value of flux, peak value of flux, peak value of flux due to any phase, due to any phase. I hope this point is clear. Confirm me once, all of you. Right. Then what is the speed at which this field will be rotating in the space, right? So space means here I'm talking about air gap. With what speed this field will be rotating is ns, and it is given by 120 into F by P. Let us consider the frequency of these three-phase currents is 50 Hertz. Then with what speed that field will be rotating in space in this case means 120 into 50 by 4. So it is something like 1500 RPM. So this is the speed at which the field will be rotating in space, right? So what is the speed at which this field will be rotating in space? Means it is rotating with a speed ns is equal to 120 F by P, and in this case it is a speed that is 1500 RPM. This is the field which is rotating with the speed of ns. So with what speed that field will be rotating in space means it is rotating with the speed of ns. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So can I once again repeat? So whenever we pass a three-phase currents into the three-phase winding, then we have seen means in the previous classes, we have three individual MMFs which are stationary and pulsating along their own axis. And the resultant of all those three individual MMFs is a rotating MMF. As that MMF is rotating, the field produced by such rotating MMF is also rotating. And I'm naming that field as the stator rotating magnetic field, or in simple, stator field. And if you open the machine and look for the stator field, you cannot see. Why? Because no field is holding a tagline that I'm calling myself as a stator field. No, it is only the imagination how the mechanism of torque is produced in an induction machine. So you have to see step by step. A three-phase supply is given, three-phase currents are flowing, a rotating magnetic field is produced. So these are the sequence of steps. You have to imagine, oh, when we give a three-phase voltage, three-phase currents are fast flowing, a rotating magnetic field is produced in the air gap. Then you have to imagine, oh, in the air gap, a field is rotating with a speed ns. And in this particular case, it is rotating with a speed of 1500 rpm. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. So I'm calling this stator as a stationary observer. So here I'm calling stator as a stationary observer. I'm calling stator as a stationary observer. Or it is something like someone is standing on the stator and watching the field. If someone is standing on the stator and watching the field, to that percent with what speed this field will be rotating, this field will be rotating with a speed of ns. It is something like this. I'm standing next to a railway track and just some 10-15 meters away from the railway track. And what I found is on the railway track, one train is passing with 100 kilometers per hour. As I'm a stationary fellow, if anyone questions me, or what is the speed of the train with respect to you, then I can see it is 100 kilometers. Why? Because I'm a stationary fellow and the train is moving with 100 kilometers per hour, then the speed of the train with respect to me is 100 kilometers per hour. So here also the stator is stationary, right? And the field is rotating in air with a speed of ns. Then if a person is standing on the stator, then with what speed that field will be rotating means it is rotating with a speed of ns. So can I give one statement? The speed of the stator field with respect to the stationary observer, the stator is ns. So this is one point to be noted. The speed of the stator field with respect to the stator is ns. Is this point clear? Confirm me. Confirm me. Right. So first point to be noted here is the speed of the stator field. The speed of the stator field with respect to WRT means with respect to stator or stationary observer is ns. So this is something like first step, but it is something like typical to imagine. It is something like difficult to imagine. Why? Because I say the field is moving. So I try to show the exact phenomena, what is happening, so that we can imagine the field is rotating. So for that, I go for another way of analysis, another way of explanation. So if we just recall, so the stator, in the stator, we distribute the conductors of three-phase windings. Right? Let us consider that I'm having some set of conductors. So these may be the conductors of all three phases. 1, 2, 3, 4, 5. And all these conductors windings, and internally the terminals like A dash, B dash, C dash are being joined, and the remaining terminals like A, B, C are brought out. A, B, C are brought out. Then through this three-phase windings, if I pass IA, IB, IC, then you know that in the stator we have the rotating poles. So what are formed in the stator core? Poles. So whenever we are having poles, what is that? You can imagine the magnetic flux lines like this. So what is the nature of these poles formed? Means rotating. So the core is stationary, the poles are rotating. So what is the speed at which these poles will be rotating? Means these poles are rotating with a speed of ns. Then what is the speed at which these flux lines are also rotating with a speed of ns? Then what is the speed at which the group of flux lines, that is the flux is also rotating, it is rotating with a speed of ns. So can I say in other way, instead of talking about MMF concept, I tell like that. So whenever we pass a three-phase currents into the three-phase winding, the rotating poles are formed in the stator core. So whenever we talk about poles, then you can see the magnetic flux lines. As these poles are rotating, the flux lines are also rotating in the air gap. the group of flux lines, the combination of the flux lines, we call it as a flux. As the flux lines are rotating, the flux is also rotating. So you can see the flux is rotating in the space. So can I imagine like this? So with three-phase currents and three-phase current windings, poles are formed in the stator core. So with poles, we are having magnetic flux lines. As these poles are rotating, the flux lines are also rotating. That is the group of flux line, the flux is also rotating. So with what speed that flux lines will be rotating is the same as the poles. So inside the stationary core, with what speed those poles are rotating, the poles are rotating with the speed of ns. Then the speed of the stator field with respect to the stator is ns. Is it clear? Confirm me all of you. Right. So you can just explain either this concept, that is the MMF concept, or you can explain with respect to this poles concept. More or less both are same. So one is something like which we cannot see, which we have to imagine. The other one is the poles we can see and the field lines we can see, and the field is also rotating. See, Baba, someone is raising the hand. Say there is no technical issue from my side. So please try to rectify from your side. I'm done. I think remaining people, please raise the hands if we are clear from my side. Yeah. So I'm clear. So maybe the technical issue from your side. Try to rectify that. Right. So first thing is over. First thing is over. What is that first thing? The speed of the stator field with respect to stator is how much ns, right? See, yesterday I told you anonymous attendee. Please try to keep your name. Please try to keep your name. See, I don't like these anonymous attendees. See, please, you have the right to ask, but don't keep your name as anonymous attendee. Please remember that. Please remember, right? Fine. So once again, what is the speed of the stator field with respect to the stator? Means it is rotating with the speed of ns. Done. Now you please tell the stator is stationary. Inside that stator, these conductors are stationary. But whatever the poles, those are formed inside the stator, they are rotating. As they are rotating, so they are cutting which conductors now? The stationary stator conductors which are in the stator slots. So once again, the stator is a stationary part. Inside the stator, we have these conductors. So whenever a three-phase supply is given to the stator, what are formed? Magnetic poles and magnetic flux lines. What is the nature of these poles? Rotating. As these poles are rotating, they are cutting this stationary stator conductors. Due to that flux cutting, what is induced in that? An EMF will be induced. In other way, in your B.Tech, you might have learned the definition for Faraday's law. What is that? Whenever there exists a relative speed or relative motion between the windings and the magnetic field, an EMF will be induced. So here you can see, these windings are stationary. These windings are stationary. So you can see these windings are stationary. What is the speed of this winding? 0. And this field is rotating with the speed of ns. Then what is the relative speed between this field and these windings? Ns minus 0, it is ens. So due to this relative speed between the field and the conductors, relative speed and the windings, what is induced in this winding? An EMF will be induced. An EMF will be induced. So once again, the stator is a stationary part. The windings which are placed in the stator slots are also stationary. But in the space, in the air gap, the field is rotating. As that field is rotating, due to the relative speed between the field and the stationary stator conductors, what is induced in the stator conductors? An EMF is induced. That is a general statement. But truly speaking, so whenever we have relative speed, what is that happening means? See, as the field is rotating, as the flux lines are rotating, so the rotating flux lines are cutting the stationary conductors. So due to this flux cutting, what is induced in the stator winding? An EMF is induced. So can I mix up these two statements and give one general statement? Can I write? So due to the relative speed between the windings and the magnetic field, the magnetic flux lines are cutting the conductors. So due to this flux cut, an EMF is induced in that windings. Is it clear? Confirm me all of you. Is it clear? Confirm me, all of you. Right. So can I write? Can I write like this? Due to the relative speed between the stationary stator windings and stator field, the stator flux lines are cutting the conductors conductors. Hence, an EMF is induced in the stator winding according to Faraday's law. Faraday's law. Faraday's law. See, as I'm using one statement called as Faraday's law here, don't say that this induction motor is working on Faraday's law. Wrong. So recently one of the student has raised this, sir. The EMF is due to that Faraday's law. Why can't we call it as Faraday's law? The machine is working on Faraday's law. No. What is that motor principle? F is equal to BIL. But the EMF here is due to induction principle. That's the reason we are calling it as Faraday's law here. Is it fine clear? Confirm me. Right. Only few what happens to other. So I told you that all has to raise. Right. So I'm giving that magnitude of that EMF. How to give that magnitude? So E for the EMF, suffix 1 for the stator side, and I'm not deriving this and it is not required also. 4.44 F1 phi1, the number of turns into the winding factor. So in this, F1 represent the frequency of induced EMF in the stator windings. Right? And this depends upon the relative speed into poles by 120. Now you please tell me which field is responsible for that EMF in the stator winding? Stator field. What is the speed at which that field is rotating? ENS. In which windings it is induced? Stator winding. What is the speed of that stator winding? 0. So can I say relative speed means we have to find out the speed difference between two quantities. So what are those two quantities? One is the field which is responsible for the EMF. The second thing is the windings in which an EMF is induced. So which field is responsible for this EMF? Stator field. And in which winding it is induced? Stator winding. I need to find out the relative speed. So it is the speed of stator field minus speed of stator conductors into P by 120. What is the speed of the stator field? Ns. What is the speed of the stator conductor? 0 into P by 120. So it is Ns into P by 120. So what is the value of Ns in this case? 1500 into poles are 4 by 120. If I do it, 50 hertz. So numerically, this frequency is which frequency? The supply frequency. So the second point to be noted here is the frequency of induced EMFs in the stator windings will be always equal to the supply frequency. So here, in case of this F1, I write it as F. So once again, due to the relative speed between the stator field and the stationary stator winding, an EMF is induced. But truly speaking, whenever there exists a relative speed, so the stator flux lines are cutting the stationary stator conductors, and due to this flux cut, an EMF is induced. So that is given by E1 is equal to 4.44 F151, right? N1 KW1, right? And in this, F1 is the frequency of induced EMF. It depends upon the relative speed between the field and the conductors. So the relative speed is Ns, and hence the frequency of the induced EMF is the supply frequency. Please confirm me if it is clear. All of you raise the hands. Right, done. So the second point is the frequency of the frequency of the frequency of the induced EMF in the stator windings is always equal to the supply frequency F. Yeah. But remember, see, my voice is lagging. Shivateja. Is it like that? Anything voice is lagging like that? So I think no, right? So please raise the hand. Everything is clear. Raise the hands once. Yeah. See, Shivateja, from my side, I am clear with the network. So maybe from your side, Shivateja, Chanda, you please try to check up, right? So what is that KW, right? Dwarakesh. So it is the winding factor. I told you already, right? Right. Shivateja. Okay, no, Baba. No problem. Baba. Right. Done. Fine. Right. Sir, videos. I'll show. Don't worry. No, don't worry. I'll show. Fine. So this is something about your so-called as the second point to be noted. Right. Done. See, this E1 is called as a back EMF. This E1 we call it as a back EMF, and also the EMF that is induced in the stator winding. So without this back EMF, there is no concept of motoring. The motor will not rotate at all. So every motor should have a generated concept, and every generator should have a motoring concept inside. So without a generation, there is no motoring. Without a motoring, there is no generation inside. So both should exist simultaneously. So unless and until this back EMF is there, there is no concept of motoring, there is no concept of power balance. So there is no power balance. So compulsorily this E1 is required for sure. When there is no E1, there is no power balance. Now let me explain the significance role of this back EMF. So what is that back EMF doing in this motoring, right? I hope this is clear. We'll see that one by one. So it is clear. Done. Now below to this, you can see the rotor who is sleeping as of now, coolly sleeping, that fellow. Even in the rotor also, in case of slip ring, we have windings. In case of cage rotor, we have bars, right? So let me number that, not number, let me use some terminology. A, B, C, D, E. As of now, these rotor conductors are also stationary. But whenever I'm giving this three-phase supply, as the stator poles are rotating, even they are cutting which conductors? The rotor conductors. Rotor conductors. In other way, you can see this is the rotor which is stationary as of now, and this is the field which is rotating now. So due to the relative speed between the stator field and the stationary rotor winding, an EMF is induced. Whenever I talk about relative speed, what is happening? As these poles are rotating, even they are cutting the stationary rotor conductors also. So due to this flux cutting, what is induced in the rotor conductors also? EMF, according to which law? Faraday's law. Once again, as of now, the rotor is stationary, and in the space, the field is rotating. So due to the relative speed between field and the stationary rotor conductors, a rotor winding and EMF is induced. That is the statement. But truly speaking, what is happening as the stator poles are rotating, flux lines are rotating, and those rotating flux lines are cutting the stationary rotor conductors. As a result, what is induced? And EMF is induced. So finally, can I say the stator flux lines are not only cutting the stator conductors, even they are cutting the rotor conductors also, and hence an EMF is induced in both the windings. Is it clear? Confirm me. Confirm me. Right. So I'll write that statement. Due to due to the relative speed between the stationary rotor windings rotor windings and stator field stator flux lines are even cutting the rotor conductors, and hence an EMF is induced in the rotor windings according to Faraday's law. Faraday's law. So whatever the EMF that is induced in the both the windings, we call it as according to Faraday's law. So here I am using E again for the EMF, suffix 2 for the rotor side, and in addition to that I am using not 0. So what does this 0 represent? Means when the rotor is stationary. When the rotor is stationary. So in all our coming classes, whenever I am using suffix 2, remember that suffix 2 is for the rotor side. And along with that suffix 2, if I am using 0, it indicates when the rotor is stationary. Please try to use this notation. So E2 naught is the EMF that is induced in the rotor winding at standstill or when the rotor is stationary. So can I use this? This is a standstill rotor EMF. I hope this point is clear. So this is given by again 4.44 F2 phi1 N2 is the number of turns, Kw2 is a winding factor. So it is not a printing mistake. As of now, which flux is responsible for that EMF in the rotor circuit? Phi1 as of now. So that is the reason it is phi1, and the remaining terms are the rotor terms. I hope this point is clear. Confirm me, all of you. Confirm me. Right. So in this, what is that F2? So F2 is the frequency of induced EMF in rotor windings. So this also depends upon the relative speed into poles by 120. Again, which flux is responsible for this rotor EMF? Stator flux. So speed of stator flux minus speed of rotor conductors into P by 120. So what is the speed of the stator flux? Ns minus what is the speed of the rotor conductors as of now? 0 into P by 120. It is Ns into P by 120. Again, this is nothing but your supply frequency. So what is the rotor EMF frequency at starting? It is nothing but supply frequency. So even tomorrow when you are coming across E2 naught, so in that, what is the frequency parameter F2? It is always equal to F. So F2 is always equal to F at starting, but not in all the cases, right? Once again, as of now, rotor is stationary. On the surface of the rotor, the field is rotating. Which field is rotating? Stator field is rotating. Due to the relative speed between that rotating field and the stationary rotor windings, the stator flux lines are cutting the rotor conductors. Due to this flux cutting, what is induced in the rotor winding? An EMF is induced. So we have used one notation, E for the EMF, 2 for the rotor circuit, and additional naught when the rotor is stationary. Then finally what we observed is the frequency of the rotor EMF at starting is always equal to the supply frequency. Is this point clear? Confirm me. Is this point clear? Confirm me. But this EMF, we cannot call it as a back EMF. Back EMF means to that winding, already there should be some voltage, and that voltage in turn should make another voltage to induce. So that is a back EMF. But in the rotor circuit, there is no like secondary voltage. Whatever the EMF that is induced, it is only E2. So it is only the EMF that is induced. So we are not calling this one as a back EMF. Only E1 we call it as a back EMF. I hope this is clear. So can I say the frequency of induced EMF in the rotor windings at starting is always equal to the supply frequency. The supply frequency. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Done. Now, only few. See, Baba, please try to be active. Right. Now, what I want to do means I want to find out the direction of induced EMF. In which conductors I need to find out the direction of induced EMF? See, one small correction. So this anonymous attendee's question is, sir, stator field is placed in the stator. Stator field is not placed, okay? Stator will not rotate now. So how stator field also rotating? Stator field also not rotate now, sir. See, I told you already, you take a watch, the daily stationary, but in that those needles, the bigger hand and smaller hand, they are moving. So here the stator is stationary. Inside that poles, those poles are rotating. So stator field is not placed, Baba. We are not placing any stator field. Please try to use the terminology. The stator field is produced by the stator poles. And what is the nature of those stator poles? Means those poles are rotating and the field is also rotating. Please try to rectify your statement. So that is the reason I kindly request you to refer my notes once or twice. Then only you try to raise the hands. It is not like blindly use your nonsense terminologies here. Okay. I never said that the stator field is placed. I told you that the stator windings are placed, right? I hope this point is clear. All of you clear? Raise your hands. Right, please. Fine. So this is something about the second part. Now what happened? An EMF is induced here in the rotor conductors. An EMF is induced. And I want to know the direction of induced EMF. So if I want to know the direction of induced EMF, which rule, which law I need to call upon means the Fleming's right hand rule. Please remember, motor means Fleming's left hand rule, generator means Fleming's right hand rule. No. Whenever there is some EMF in the conductor, and if you want to know the direction of induced EMF, right hand rule. Whenever a current carrying conductor is placed under magnetic field force, left hand rule. So this force can happen in generator or this EMF can happen in motors. So please don't mix up. So EMF means right hand rule. Force means left hand rule. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So can I say the direction of the direction of the direction of induced EMF in the rotor conductors can be found by using Fleming's right hand rule. Right hand rule. See, when I was explaining this Fleming's right hand rule, I have taken two cases. What are those two cases? If field is stationary, and in that stationary field, if the conductor is moving, then you can apply Fleming's right hand rule directly. In the second case, if the field is moving and the conductors are stationary, then in that case also an EMF is induced, but you cannot apply the Fleming's right hand rule directly. Then if you want to apply the Fleming's right hand rule there, you have to imagine that the conductors are moving in a direction opposite to the field to know the direction of induced EMF. So this point, I have spent nearly half an hour to discuss that. I hope you remember this. All of you raise the hands. Right. Now you please tell Baba. So I consider one conductor A here, one conductor A or C. Let me consider one conductor C here. So in that conductor C, I want to know the direction of current is into or the direction of current is outwards. Right? I'll take this conductor C. Conductor C. Then what is the direction of that magnetic field? See, it is raining heavily here. Sometimes the power may go. So I'll try to go for an alternative. Don't worry. So I have that UPS. I'll go for an alternative. Don't worry. Even if suddenly cut, don't worry. I'll come back. So please remember that, right? Is it clear? Raise the hands once. See, I told you clearly, some Murli, generator principle is left hand na. No, Baba. See, it is not the generator principle. Generator works on Faraday's law. That means if you want to have EMF, the conductor should be moved under a magnetic field. If you want to know the direction of induced EMF, right hand rule. Morley, please try to understand, right? It is not like left hand rule, right? So motor is, the direction can be left hand, and in case of generator, the EMF can be right hand. Morley, understood? Please, Baba. Right. Good. So now I want to know the direction of induced EMF. So in which direction the field is moving? Downwards. And in which direction the field is moving? Clockwise. The direction of the field is downwards, and in which direction the poles are moving? Clockwise. Then to apply the Fleming's right hand rule, we have to assume that the conductor is moving in counterclockwise direction. It is the direction of the field. This is the direction of the motion of the conductor. Then if I apply right hand thumb rule, so this is the direction of induced EMF. It is outwards or inwards? It is outwards. You can apply the same thing. So the direction of induced EMF in this conductor is outwards. It is outwards. Is it point? Is this clear? Confirm me all of you. Is it clear? Confirm me all of you. So this is not the first time I'm discussing. This was already discussed in the previous classes. So here, the direction of induced EMF will be dot. So this is up to the direction of induced EMF. Now the rotor circuit is closed or open now? The rotor circuit is closed. You can see here the rotor circuit is closed. When the rotor circuit is closed, the EMF which is induced, which is induced, will establish a current, and this current will flow in the windings. You know that windings are nothing but coils. Coils are nothing but turns. Turns are nothing but conductors. And where those conductors are there, those conductors are exactly under the magnetic field. So to due to this, what is there on the conductors, a mechanical force will be acting. Once again, as those poles are rotating, they are cutting the rotor conductors, EMF is induced. And as the circuit is closed, the induced EMF will circulate current, and this current is flowing in the conductors, and these conductors are already under the magnetic field. Then according to Lorentz law, when the current carrying conductors are under the magnetic field, so those conductors will experience a force, and due to this force, the rotor has to rotate, right? So this current is a induced current, or this current is a supplied current. This current is a induced current. Is this point clear? Confirm me. Confirm me. Right. So can I say like this? Can I say like this? As the rotor circuit is closed, rotor circuit is close, the induced EMF in the rotor windings establishes a current, and this current flows in the rotor conductors which are under the magnetic field, and hence these conductors experiences a force experiences a force according to Lorentz law. What is that Lorentz law says? That already we have seen, if a current carrying conductor is under the magnetic field. So Lorentz never said that whatever the current that flows, it is because of your supplied current or it is due to induced the current. It is no way. So a current carrying conductor should be under magnetic field. So that current may be from a separate source, or that current may be induced current. He is not bothered about that, right? According to Lorentz law, Lorentz law, Lorentz law. So the conductors experiences a force according to Lorentz law, and hence rotor starts rotating. A rotor starts rotating. Once again, so due to this flux cutting action, what is induced in the rotor conductors? EMF. As the rotor circuit is closed, the induced EMF is circulating current, and this current is flowing in the rotor conductor under the magnetic field. And as these current carrying conductors are under the magnetic field, so those conductors are experiencing a force, and due to that force, see, right? See, from my side, it is clear. You try to check, right? So due to that force, the rotor will start rotating. Is it clear? Confirm me all of you. Confirm me all of you. Right, done. Right. So here, so can I say I2? It is the EMF that is induced in the rotor by the impedance. So this current is flowing in the conductors, and these current carrying conductors are under magnetic field, and these conductors will experience as a force. These conductors will experience as a force. So finally, if anyone questions you, what is the basic principle of induction motor? Then you have to say the Lorentz law. So what is that Lorentz law says? That F is equal to BIL. So what is that BIL states that if I am having a conductor of finite length L, and through that conductor if I am passing a current of I amperes, and if this set current carrying conductor is placed under a magnetic field, then that conductor will experience as a force. So this is what the Lorentz law said. Then in case of induction motor, in order to meet the first condition, What is that first condition? B. B, we are taking a three-phase supply and we are passing that three-phase supply into that three-phase winding. Then we can see a rotating field is produced. The first condition is over. A rotating magnetic field is produced. The first condition is over. The second is I need a conductors of finite length. So where we are placing those conductors of finite length in the rotating part called as a rotor. Second condition is also over. Third condition is that conductor should carry current. So for that we are not using an external source to supply the current, but whatever the flux which is rotating, as it is cutting those conductors and EMF is induced, as that bars are closed or the circuit is closed, that induced EMF is circulating a current and these current carrying conductors are experiencing a force, and due to this that rotor will start rotating. The rotor will start rotating. Is this point clear? Confirm me. Right, done. So like that, the rotor will start rotating, right? Done. Now the question comes, is that rotor core is experiencing the force or the rotor is experiencing the rotor conductors are experiencing the force, right? See, Mr. Murali, sir, NS and NR is equal now, sir. See, I never use any terminology called as NR as of now. I don't know from where you got NR. The second point, both fields are same direction, sir. I never said what is the second field as of now. I never said any field as of now. So please, my humble request, hold down. You may know the subject, but my 90% students may not know the subject. So I'm just keeping those people in mind. I'm trying to go in a flow. So I hope you understood morely, right? Try to understand. See, I never said anything, right? NR, I don't know as of now. I don't know what is the second field as of now, right? Please remember me, right? I'll try to explain. Just hold me for some time, hold me for some time, right? Done. Once again, so one student told, what is BIL? See, according to that Lorentz law, if the current carrying conductors are placed under the magnetic field, those conductors will experience a force. If you remember, in case of a DC motor, I don't know which day it is, the day before. In case of DC motor, if you remember, even there also, what is the condition to have motoring means the same thing, F is equal to BIL. The same condition F is equal to BIL. I told you the same condition F is equal to BIL there. Right? How this condition B is there means, so for that we are taking a field winding and through that we are passing a field current. Then you can see the magnetic poles are formed. The first condition is over. The magnetic poles are formed. So this one is the magnetic poles are formed. The first condition is over. What is the second condition? I need a conductors of finite length, where we are placing those conductors of finite length in the rotating part called as a armature. The second condition is also over. What is the last condition? Those conductors has to carry current. So for that we are taking a separate source, and using this separate source we are passing a current into these conductors. Then you can see these are the current carrying conductors placed under a magnetic field, and these conductors are experiencing a force, and due to that that armature will start rotating, right? I hope this point was already explained in the previous classes. Please confirm me, raise the hands. Right. So if anyone questions you, array, that Lorentz law, when it is obeying there, what is the nature of that field? It is a stationary field. But in case of induction motor, what is the nature of that field? A rotating field. So Lorentz never said that. So if you want to have force on the conductor, I need a constant stationary field or a rotating field. The field may be rotating or the field may be stationary. I'm not bothered about. But the current carrying conductor should be under the magnetic field. It may be stationary field or it may be rotating field. It has to be under a magnetic field. Then I can say there is a torque. So here today, if you just look at F is equal to BIL condition, what is the first condition I need to satisfy here? It is B. So in order to produce magnetic field, we have taken three phase windings and we have passed three-phase current, then you can see the poles are formed. And what is the nature of those poles? Rotating. The first condition is over. The second condition is I need a conductor of finite length, where we are placing those conductors of finite length on the rotating part called as a rotor. Second condition is over. What is the third condition that need to be satisfied? Those conductors has to carry current. So how we are supplying those current means not using an external source, but that current is due to induction. How? As those poles are rotating, they are cutting the rotor conductor EMF. As the circuit is closed, they are carrying the current. As those conductors are already under the magnetic field, they are experiencing the force. So here also BIL conditions are being satisfied. So finally, this motor works on Lorentz law. I hope this point is clear. Confirm me, all of you. Right. So I'll just, so can I say as the rotor circuit is closed, the induced EMF is circulating current. As these current carrying conductors are already under the magnetic field, so these conductors will experience a force, and due to that force the rotor will start rotating. Now the question comes, three questions. In which direction the rotor rotates? If I'm assuming the field is rotating clockwise, will the rotor also rotates in the same direction clockwise? Second point, with what speed the rotor will rotate? As the field is rotating with ns speed, will the rotor also rotate with the speed equal to ns or less than ns? Second question. Third one, if it is less than ns, who is deciding that less than ns? What is the meaning of that? Say, if the field is 1500, if the rotor speed is 1440, so why it is 1440? Why can't be 1400? Why can't be 50? Why can't be 10? So who is deciding the difference? Right? We are trying to answer to these three questions. What are those three questions? One is, in which direction the rotor will rotate? Second one is, with what speed the rotor will rotate? Third one is, who decides that? Right? What are the questions we are supposed to have? In which direction the rotor will rotate? Which direction the rotor will rotate? Already you know which direction the rotor will rotate. A rotor will rotate. A rotor will rotate. Second, with what speed the rotor rotates? With what speed the rotor rotates? A rotor rotates. Then who decides the speed? Who decides the speeds? The speed. Right? So these are the three questions which we are supposed to answer, right? Fine. See, anonymous attendee. Sir, stator winding is not rotating means how will be the rotating the stator field? See, windings are different, field is different. So the field which is produced by the three-phase stator winding will be rotating. Mr. Anonymous attendee, please refer to my RMF concept. Please try to refer to my the so-called as the concept of rotating magnetic field. Then you'll understand. All right, done. Fine. So Morley, sir, less than ns induction motor is not self-starting. Right, done. So in which direction the rotor will rotate? So if I want to know in which direction the rotor will rotate, then I need to apply these two rules. One is I can apply Fleming's left hand rule to know the direction of the force. The second one is I can apply the Lenz's law to know the direction of the force or to know the direction of rotation, right? So the first answer is to know in which direction the rotor rotates, we apply either Fleming's right hand rule or Lenz's law. Just 1 second. I'll try to show when the windings are stationary, how the field is rotating. Just 1 second. Content is not supported, cannot connected to AirPlay, so we cannot see. So you just refer that, you can understand why, because it is not connecting, please. So this media is not connecting, right? You can see the windings are stationary, but the field will be rotating. Is it clear? All of you confirm me? Confirm me, all of you. Raise the hands. Right. Now I need to find out in which direction the rotor has to rotate. So to know that, I'll be applying Lenz's law. After that, we'll be applying left hand rule, not right hand rule, left hand rule. Sorry, printing mistake. Left hand rule, right? Done. Thank you, Baba. Now, what is that Lenz's law says that? What is that Lenz's law says that? The effect should oppose the cause. What is that Lenz's law says that? Lenz's law states that the effect should oppose the cause. Should oppose the cause. Now, first of all, I'll be finding out what is the effect. Then after that, we'll see who is the cause for that effect. After that, we'll see how that effect will oppose the cause. Now, please see here. Initially, the rotor is stationary. Initially, the rotor is stationary and the rotor is sleeping, snoring and sleeping. As it is sleeping, there is no torque acting on the rotor. If there is a torque, the rotor would have started rotating. The rotor is stationary and sleeping. Now we are giving a three-phase supply to the stator. Rotor is sleeping. So because of those three-phase supply, three-phase currents are flowing, rotor is sleeping. Because of those three-phase currents and three-phase winding, rotating poles are formed in the stator core. Rotor is sleeping. As these poles are rotating, the flux lines are also rotating. Rotor is sleeping. As the flux lines are rotating, they're cutting the stationary stator conductor and also the rotor conductor. Rotor is sleeping. Due to this flux cut, what is induced in the rotor conductors and EMF is induced. Rotor is sleeping. As the rotor circuit is closed, the induced circulating current. Rotor is sleeping, right? So due to, is clear. Once again, rotor, I can understand. If all are raising the hand means I can understand. Right. See, once again, rotor is initially sleeping. When the rotor is initially sleeping, I'm giving a three-phase supply to stator. Then due to that three-phase supply, what are flowing in the windings? Current. And due to that currents, what are formed in the core, stator core poles? As we are having poles, what are the flux lines? As these poles are rotating, the flux lines are also rotating. They are cutting stationary stator conductor and also the rotor conductor. What is induced in both? EMF. As the rotor circuit is closed, the induced EMF is circulating current. As these current carrying conductors are already under the magnetic field, so these rotor conductors are experiencing the force. The rotor conductors are experiencing the force, and hence the rotor conductors wants to fly away. The rotor conductors wants to fly away. But as the rotor conductors are locked in the rotor slots, as they cannot fly away, so they are making the rotor, please leave, we want to fly. Please leave, we want to fly. But the rotor cannot leave, so there is a force acting on the rotor to turn. There is a force acting on the rotor to turn. There is a twisting force acting on the rotor to turn. The rotor will wakes up. Or why should I turn now? So what is that effect? Means it is the turning effect. It is the turning effect, or it is the twisting effect, and this we call it as torque. So what is the effect? Means it is the torque which is acting on the rotor. So because of this torque, the rotor has to rotate. Is this point clear? What is effect here? Torque. Is it clear? Raise the hands. Now the rotor will wakes up. Arey, what is happening? Why should I wake up? Why should I turn? Why should I twist? Then the rotor diagnoses that the rotor conductors are experiencing the force. Are how? Why? Because the rotor conductors are carrying current. Or how? The rotor is not separately excited. How the rotor conductors are carrying the current? Why? Because there is some EMF inducing the rotor conductors, right? Hari, how? Why? Because these conductors are being cut by the magnetic flux lines. Which magnetic flux lines are cutting this rotor conductor? Stator magnetic flux line. Why the stator flux lines are cutting the magnetic rotor conductors means due to the relative speed. Why? Those poles are rotating and these conductors are stationary. Due to the relative speed, those flux lines are cutting the stationary rotor conductor. So who is the main cause for the torque? Means the relative speed between the stator field and the rotor conductor. Due to the relative speed, the flux lines are cutting the rotor conductor, EMF is induced, current is circulating, current carrying conductors are placed under magnetic field, the conductors are experiencing the force. So who is the cause? Means the relative speed between the field and the rotor conductors. So relative speed between the stator field and a rotor conductors. Rotor conductors. Rotor conductors. Is it clear? Confirm me. Is it clear? Confirm me, all of you. Right. So the rotor can sleep again. Why? Because the intention of the rotor is always to sleep. So the rotor is as lazy as you people. The rotor wants to sleep always. If the rotor has to sleep always, then there should not be any torque acting on the rotor. For no torque, there should not be any force acting on the conductors. For no force, there should not be any current flowing in the conductors. For no current, there should not be any EMF inducing the conductor. For no EMF, the stator flux line should not cut the conductors. For no flux cutting, the relative speed has to be zero. To make the relative speed zero, then the rotor will rotate in the same direction as the field. Right? It is something like this. Say you are sleeping in the morning, it is a chilled morning, and one of your friend came with a chilled water, and that fellow has poured that chilled water on your face, right? Then when that fellow has poured chilled water on your face, then immediate effect is you wake up. Then you find the target, your friend who has poured the water. In order to kick that fellow, in which direction he will start turning? In the same direction. So here also, who is responsible for this turning effect? The relative speed between the stator field and the rotor conductor. As those stator poles are rotating, they are cutting the stator rotor conductors. EMF is induced, current circulate, force acting, and there is a torque acting. So when this torque will be zero, means if the relative speed is made zero, to make the relative speed zero, in which direction the rotor will start rotating, the rotor will try to start in the same direction. Is this point clear? Confirm me. Confirm me, all of you. Right. So can I say to make to make the relative speed between the stator field and the rotor conductors or rotor zero, the rotor starts rotating in the same direction as stator field. See, one of the student, again the same anonymous attendee. Sir, why can't we use Fleming right hand rule? See, I told you day one only. Law and rule are true. Theory may be true or false. So by conducting some experiment, see, if I take the field, what happened? People are raising their hands. Right. Okay, I can understand. Just I'll come back. Now it is clear, all of you? Clear? Right. See, I told you that while we are defining any law, say Faraday's law, whenever a conductor is moved under a magnetic field, an EMF is induced. So this is a law which is demonstrated practically. Experiment is done, the result is seen. If anyone questions me, sir, why can't we have an EMF with a stationary conductor? Means you can see there is no relative speed, there is no flux cutting, there is no EMF induced. And if I connect a voltmeter across those terminals, the voltage will be zero there. That is the reason I can say the field has to be stationary and the conductors has to be moving. Similarly, and if I connect an ammeter and if I see the direction of current, then that is matching with Fleming's right hand rule. So that is the reason we use Fleming's right hand rule for knowing the direction of induced EMF. Similarly, if a current carrying conductor is placed under a magnetic field, in which direction the conductor moves, we'll apply Fleming's right hand rule. So these are basing on the experimental result we try to apply. It is not my statement or it is not some other statement. Is this point clear? Confirm me. Confirm me, all of you. Right, done. So to make the relative speed between the stator field and the rotor conductors zero, 1 second. So to make the relative speed zero, in which direction the rotor has to rotate means the rotor has to rotate in the same direction. Same direction. If the rotor rotates in the same direction, the relative speed will decrease. When the relative speed decreases, the flux cuttings will decrease. When the flux cutting decreases, the EMF decreases. When EMF decreases, the magnitude of force decreases. When the magnitude of force decreases, the torque magnitude decreases, and the rotor will have a hope that it can sleep again. It can sleep again. Is it clear? Confirm me. Confirm me. Right. To make the relative speed between the stator field and the rotor conductors or rotor zero, the rotor starts rotating in the same direction as the stator field. Right. Done. Or I can apply Fleming's left hand rule. What is that Fleming's left hand rule? Fleming's left hand rule. I'll take this conductor again. I'll take this conductor again. C. And with respect to that conductor, I'll find out the direction of force. So here, this is the conductor C. What about the direction of the magnetic field? The direction of the magnetic fields are downwards. Downwards. In which direction that the currents are flowing, induced currents, it is something like outwards. Outwards. Then you can see field is downwards. I'm having left hand rule. The current is inwards. Then in which direction the force will be acting is the force will be acting in this clockwise direction. So you can see the individual forces on the conductors will be clockwise. So this force will be clockwise. This force is also clockwise, clockwise, clockwise. And the resultant of all these forces will try to make the rotor to rotate in clockwise direction. So either you can apply Fleming's left hand rule, I can apply Lenz's law. Once again, I'll repeat. The rotor is initially resting, the rotor is initially sleeping. But whenever we give a three-phase supply, the poles are formed in the stator core. As the poles are rotating inside the stationary stator core, so those flux lines which are there in the air gap, they start rotating. As they are rotating, they are cutting the rotor conductors and EMF is induced. As the rotor conductors are closed, the induced EMF will circulate a current. The current carrying conductor placed under a magnetic field will experience a force, and due to this force, the rotor has to rotate. The rotor has to rotate. That means what is the effect means the turning effect. The rotor has to turn. It is a turning effect. Turning effect. So who is the main cause for this? A turning effect means the relative speed between the field and the rotor conductors. If I want to make this turning effect to be zero, the relative speed has to be made zero. So to make the relative speed zero, in which direction the rotor has to rotate means the rotor has to rotate in the same direction as the stator field, and hence the rotor moves, the rotor turns to rotate in the same direction. This is one way. Or I can apply the Fleming's left hand rule. What is that Fleming's left hand rule? I have a conductor, and what is the direction of magnetic field on that conductor? It is downwards. Whatever the current that is induced is coming out or going. So it is something like this, coming out. Just printing mistake. It is coming out. The current is coming out. Then if you apply the this left hand rule, field is downwards, the current is coming out. In which direction the force will be acting? The force will be acting in this clockwise direction. Like this, the rotor will try to rotate in clockwise direction. So you can apply Fleming's left hand rule, or you can apply the Lenz's law. Is this point clear? Confirm me. Confirm me. Right. So first question, first answer is over. What is the first question? In which direction the rotor rotates? The rotor rotates in the same direction as the field. Of course, the same thing we might have seen in the last class also. The rotor chases the stator field. That means the rotor will rotate in the same direction. The first question is over. What is the second question? With what speed the rotor can rotate? The maximum speed the rotor can rotate is ns. The maximum speed the rotor can rotate is ns. Right? Fine. 1 second, some disturbance. Right. So with what speed the rotor will rotate? I'll tell you one thing. I'll tell you one thing. I'll tell you one thing. Right. Now, with what speed the rotor will rotate? The maximum speed the rotor can rotate is ns. Now, will the rotor will rotate with the speed ns, or it will rotate with a speed less than ns? Less than. See, I'll give an example. What does that mean? See, I'm standing next to a road. Alhamdulillah. 1 second. So I'm just disconnecting and connecting. Right, done. Now you please confirm everything is fine now. Video and other things are fine. Right, done. See, let me cross check every time. Why? Because you should not again tell. So there is a network issue. So when I move this, it is good. Now, see, I'm standing next to a road. When I'm standing next to a road, I have seen one scenario. What is that? There is one bus which is moving with 10 kilometers per hour, and a person is chasing that bus. And finally, he catches the bus. He caught the bus. Then what is the relative speed between that bus and that person means zero. Why? Because as that bus is moving with 10 kilometers per hour, the speed of that person is also 10 kilometers per hour. The relative speed between those two will be zero. Is this point clear? Confirm me once. Right. Now say the field is rotating with ns. The rotor also rotate with the speed of ns. Say I'm talking. The rotor will also rotate with the speed of ns. Then the field and the rotor conductors are stationary. Why? Because the rotor is able to catch the stator field, and the relative speed between these two is zero. When the relative speed between these rotor conductors or rotor and the stator field is zero, there is no concept of flux cutting. When there is no concept of flux cutting, there is no EMF induced in the rotor conductors. When there is no EMF induced in the rotor conductors, there is no current flowing in the rotor conductors. When there is no current flowing in the rotor conductor, there is no force acting on the rotor conductors. When there is no force acting on the rotor conductor, there is no torque acting on the rotor conductor. When there is no torque, the rotor will sleep. When the rotor sleep, then the rotor will slow down. The rotor will slow down. So it never runs. It never runs with a speed equal to ns. Why? Because if it runs with a speed equal to ns, the torque at that speed will be zero. So it will not develop any torque when the rotor speed is equal to the field speed. So that is the reason the rotor speed has to be always less than ns for a torque production. Why? Because if the rotor speed is less than ns, so there exists a relative speed, then there will be a flux cutting, there will be an EMF, there will be a current, there will be a force, there will be a torque, there will be a rotation. So for that, the rotor should always rotate with a speed less than ns. It never runs with a speed equal to ns. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So can I give a statement for say, if the rotor is rotating with a speed equal to ns, then the relative speed between the field and the rotor conductors, it is something like a person is chasing the bus and he caught the bus, he catches the bus, the relative speed is zero. Here the rotor starts rotating and finally if it catches the synchronous speed, the relative speed will be zero, flux cuttings will be zero, EMF will be zero, current will be zero, force will be zero, torque will be zero. When there is no torque acting on the rotor, there is no concept of rotation. The rotor cannot rotate, it will slow down. So the rotor has to rotate with a speed always less than ns, right? So if the rotor rotates with a speed equal to ns, the relative speed between field and rotor conductors is zero, no EMF, no current, no force, and hence no torque, no torque, no torque. Therefore, rotor rotates with a speed always less than ns. That is nr. So nr, n means speed we are using, r means rotor is always less than n, the field speed. So this is the second point. So with what speed the rotor will rotate means if anyone questions you, then you have to tell that the rotor always try to rotate with a speed less than ns. If the question is why can't it rotate with a speed equal to ns, if it rotates with a speed equal to ns, the relative speed between the two fields will be zero and hence the flux cuttings will be zero and hence there is no concept of torque production, right? See, this anonymous attendee, I don't know whether he's having a subject or he's not having a subject. So I don't know who is he, what is his name, right? Please try to come out with a name. Sir, as the same number of poles, is there any chance of magnetic field? There is no concept of magnetic field locking. Why there is no field means that is what I'm trying to tell. Just wait, right? So he is very curious to throw the questions which are irrelevant to the subject. Just let me finally conclude. So in which direction the rotor will rotate? The rotor will rotate with a speed equal to ns, right? And always less than ns. Is this point clear? Confirm me all of you. Confirm me all of you. Right. So as you can see, the rotor speed is always less than ns. These motors are also called as asynchronous motor. See, what is the meaning of asynchronous means other than synchronous. The rotor speed is always other than ns. It never be equal to ns. If it is equal to ns, the relative speed will be zero, torque will be zero. The rotor will not rotate. So can I say as the rotor rotates with a speed always less than ns, this induction motor is also called as asynchronous motors. So asynchronous is a single term. Asynchronous means other than synchronous motor. It will always rotate with a speed less than ns. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. Now the second question is also over. Third question is with what speed it will rotate is done. Sir, if the synchronous speed is 1500 rpm, you told that it is less than ns. Yes, I agree. It is called as 1440 here, maybe. Why? Because when compared to ns is 1500, 1440 is less than. Is it 1440? Don't know. Why? Because 1440 is less than ns. So is it 1400? Don't know. Is it 1000? Don't know. Is it 500? Maybe. Is it 100? Maybe. Don't know. Maybe 1? Maybe. Don't know. Why? Because when compared to 1500, whatever the values I told are all less than that ns only. So what do you mean by less than? Who decide that less than speed? Less than speed. So it depends upon the load angle. What is the meaning of load angle? See, if you imagine a fan on your head, so it is not rotating. If my question goes, why it is not rotating, means you blindly give the answer that someone is opposing the rotation. Who is that someone is opposing the rotation? Means the frictional forces. So because of the frictional forces which are acting in opposite direction, the fan is stationary. When that fan can rotate, means if the motor which is used inside, if it is producing a torque to cancel out this frictional torque, if the magnitude of the developed torque and the magnitude of this frictional torque both are same and opposite, then the fan will try to rotate. Is this point clear? Is this point clear? Right. Once again I repeat, assume that the fan is not operating, it is not rotating, it is stationary. If my question why it is stationary, means there is someone who is opposing. Who is opposing means it is the frictional forces which are opposing. So if I want to make that fan to rotate, then I have to give some supply. Then that supply has to produce a torque, and the torque has to compensate that frictional torque, and because of that, the fan has to rotate. Is this point clear? Confirm. Once again, finally, raise the hands. All right, fine. Now I am considering a induction motor, three-phase induction motor. The induction motor is not loaded. It is not loaded. So if it is not rotating, means who is opposing that? Means the friction, the frictional torques. So if I want to make that shaft to rotate when there is no load, then the motor has to produce a torque turning effect to compensate that frictional torque. So for torque, the motor should receive some power. For power, the motor winding should carry some current. For current, there should be some EMF. For EMF, there should be some relative speed. So this relative speed will be based on the load on the motor. If there is no load, then the load on the motor is very less. The torque on the motor is very less. To compensate this torque, the motor torque should be less. For that, the power should be less. For that, the current should be less. For that, the EMF should be less. For that, the relative speed should be less. For that, the rotor will rotate with a speed closer to ns. Is it clear? Is it clear? Right. Once again, I repeat. See, the three-phase induction motor is not loaded. There is no load on the motor. So what is the magnitude of that load torque? Means it is almost zero, almost neglected. It is very less. If I want to make the rotor to rotate, then the motor has to produce a torque which is balancing, which is compensating that load torque. So to compensate that load torque, so the motor has to produce a torque. For that it need a power. For that it need a current. For that it need a voltage. For that there should be some relative speed. As there is no load As the load torque is zero, then as the load torque is very, very less, then the required motor torque should be less. For that, the power should be less. For that, the current should be less. For that, the EMF should be less. For that, the relative speed should be less. Then the rotor will be rotating with a speed closer to ns, very close to ns. Whenever you're increasing the mechanical load or opposition, then this motor torque has to increase. When this motor torque has to increase, the power has to increase. For power has to increase, the current has to increase. For current has to increase, the EMF has to increase. For that EMF has to increase, the relative speed has to increase. For that, the rotor will slow down so that the relative speed will increase. So who is deciding the speed? Means the load on the motor. The load on the motor. More is the load, the speed will be very away from the ns. If the less is the load, the speed will be very closer to ns. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Right. Let us see some questions people have raised. Sir, but in synchronous machine, it will be equal to ha baba. So in synchronous machine, please remember it is a double excited motor. So the stator field is rotating with ns, and will make the rotor to rotate with the ns, then we'll give an excitation, then we'll make the stator field and the rotor field to get locked. So whatever the current that flows in the synchronous motor, rotor winding is separately excited. So these two currents will make the field to get locked. But whereas in case of induction motor, the rotor is not excited with a separate source, but that current will be induced due to induction. Further, there should be some relative speed. Further, the rotor speed should be always less than ns. Is it clear? Anonymous attendee, is it clear? All of you, is it clear? Right. Fine. See, next. So one more. Sir, there are same number of poles. There is a chance. That's what I told you, that the magnetic locking will take place when these stator poles and the rotor poles are getting locked. But here the rotor poles are formed due to induced currents. And these currents will be induced only when the rotor speed is less than ns. When the rotor speed is less than ns, this rotor field will produce. When the rotor speed is equal to ns, there is no concept of rotor pole. There is no concept of magnetic locking. Is this point clear? Vinay Kumar Chari. Right, done. Right, don't worry. Right. Fine. I'll not see now. Okay, done. Fine. So finally, so who decides the relative speed? Means it is who decide the speed of the motor, means it is the relative speed between the stator field and the rotor conductor. Who decide means the load on the motor. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. Right. So it is the load. It is the load. So 3 questions and 3 answers. Right. Once again, I'll go back. Please imagine. Go back. See, whenever a three-phase supply is given to the stator winding, then you can see the rotating poles are formed in the stator core. As these poles are rotating, the magnetic flux lines in the air gap will also rotate. These magnetic flux lines will cut the rotor conductors, EMF is induced. And as the rotor circuit is closed, this induced EMF will circulate a current. And as the current carrying conductors are under the magnetic field, so these conductors will experience as a force, and because of that, this rotor starts rotating. In which direction the rotor will start rotating means in the same direction as the stator field, to reduce the relative speed between the stator field and the rotor conductors. With what speed it will rotate means it will rotate with a speed less than ns. It cannot rotate with a speed equal to ns. Who decides that less than ns means the load on the motor? If the load on the motor is zero, no load, the speed will be closer to ns. If the load on the motor is there, then the speed will be little bit away from the synchronous speed. Like that, the motor will try to rotate. Is it clear? Confirm me, all of you. Confirm me, all of you. So finally, can I say the rotor rotates? The rotor rotates with a speed less than ns in the same direction as stator field based on the load on the motor. Load on the motor. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. So if anyone questions you, what is the speed of rotor with respect to stationary observer? See here, the stationary observer is the stator or something like you are standing on the stator. Inside the stator core, these poles are rotating with a speed of ns. And in the air gap, this rotor is chasing and it is rotating with a speed of nr. So with respect to the stationary observer, what is this speed ns? With respect to this, what is this speed nr? It is something like this. So these are the two railway tracks. So you are standing here. On this railway track, there is one train which is moving with 100 kilometers per hour. On this railway track, there is one more train which is moving with 90 kilometers per hour. Then what is the speed of first train means 100 kilometer. What is the speed of the second train means 90 kilometers per hour. Will agree with me? Will agree with me, all of you? Right. Then what is the relative speed between the first train and the second train means 10 kilometers per hour. Will agree with me? First train and second train. Raise the hands. What is the relative speed between the first train and second train? 100 minus 90, 10 kilometers per hour. Will agree? Please tell me. Raise the hands. Right. What happened? What is the relative speed between the two trains? This is moving at 100 kilometers per hour and this is moving at 90 kilometers per hour. What is the relative speed between these two? 10 kilometers per hour. Is it clear? Confirm me. Raise the hands. What happened? Yeah, 10 kilometers per hour. Absolutely correct. All of you raise the hands. If it is 10 kilometers per hour, raise the hands. Right, done. So it is 10 kilometers per hour. I hope this is clear, right? Done. Now the question comes. So who is standing here? The observer is standing here. So with respect to stationary observer, inside the stator core, the field is rotating with a ns, and in the air gap, this rotor is rotating with a speed of nr. So the speed of the stator field with respect to stator is ns. The speed of the rotor with respect to stator is nr. Next point is the speed of rotor with respect to the stationary observer. Stationary observer is nr. nr. I hope this is clear. Confirm me once. All of you raise the hands. Right. Done. Now your working is not over. Only 50% is over. Still it is pending 50%. Now see, I'll take the same example. Say you are standing next to a road. There is one bus moving with a 10 kilometers per hour, and there is a person chasing with 9 kilometers per hour. Is it possible for that person to catch that bus? No. Then you can use one terminology, that person has slipped the bus. That person has slipped the bus. So here also the rotor never runs with synchronous speed. It is falling behind the synchronous speed. That difference we call it as slip or the slip speed. So it is the slip which is nothing but ns minus nr rpm. So for example, if nr is equal to say 1440 rpm, then what is the slip? It is 60 rpm. 60 rpm. So can I say the rotor is falling behind the synchronous speed by 60 rpm? But I don't know that 60 rpm is very closer or it is far away from that ns. Why? Because I'll take one example and from that I'll come back to that. What is that? See, I'm having a transmission line and I'm having a transmission line. Say the drop in this transmission line is something like 100 volts. The drop in the transmission line is 100 volts. If my question is that 100 volts is a bigger drop or that 100 volts is a smaller drop, if I raise the question, there is no answer for that. Why? Because if someone says, sir, this 100 volts is a bigger drop, very huge drop, if you say, then I say the sending end voltage is 10,000 volts. Then you will say, no, 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 sir. Sir, with respect to the 10,000 volts, that 100 volts drop is neglected. It is very small drop. So instead of that, if you say, no, 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 sir, this 100 volts is a very small drop, if you say, then I say the voltage here, it is 100.1. No, sir, if that is the case, the voltage is a very big drop. So it is not practically possible without knowing the sending end voltage to tell that 100 volts is a huge drop or it is a small drop. It is not possible. In that case, if I represent like this, 100 by 10,000 into 100, it is 1%. If I say the drop in the transmission line is 1%, 1 per unit, then which one is carrying the correct meaning is 1 per unit. Then in that case, I can say that 1 per unit drop can be neglected. So that is the reason we represent the line drops in per unit instead of the actual values. If I want to know the actual values, the base values will be given. From that, we can calculate the actual values. So from this just small example, you can see which one is having a correct meaning of the drop, means is a per unit drop or it is something like actual drop. So it is a per unit drop. Is this point clear? Confirm me all of you. So here also we don't represent this slip in RPM. Why? Because so this RPM may not give whether the rotor is very closer to NS or it is away from NS. So that is the reason we represent the slip in per unit. We represent the slip in per unit. So what is that per unit slip? Percentage per unit slip. Per unit slip is equal to NS minus NR by NS into 100. If that is the case, in this it is 1500 minus 1440 by 1500 into 1440. If that is the case, the percentage is 4%. That means the rotor is falling behind the synchronous speed only by 4%. That means it is very, very closer to synchronous speed. 96% it is closer to NS. Only 4% it is falling behind. The rotor is falling behind the synchronous speed by only 4%. 96% it is very close. So which one is the best way of representing the slip means in per unit? So that is the reason we represent the slip in per unit. Is this point clear? Confirm me all of you. Confirm me all of you. Right. Now you know that nowadays we are having fill in the blanks. Fill in the blanks. If the same question is asked, or what is the slip dash RPM, then if you represent it as a 4%, it is wrong. But if the same question is asked, what is the percentage slip? If you write 60, it is wrong. So that is the reason tomorrow in your examination, please try to see the question properly, whether the slip is represented in RPM or whether the slip is represented in per unit. Basing on that, you please try to answer. Is this point clear? All of you confirm? Right. Done. Done. Right. Now, what is the range of slip for induction motor? What is the range of slip for induction motor? What is the range of slip? See, at starting, NR is equal to 0. When NR is equal to 0, what is the value of slip? 0. 0%. 0 or 1, sorry. So S is equal to NS minus 0 by NS. So it is 1 per unit. At synchronous speed, Nr is equal to Ns. Then slip will be Ns minus Ns by Ns. So that is 1. So that is 0. Then what is the range of slip means? It is 0 and 1. But the slip cannot be equal to 0. Why? Because it never runs with a speed equal to ns. So what is the range of slip for an induction motor? Is it is between 0 to 1, but it can never be equal to 0, but it can be equal to 1. Is this point clear? Confirm me. Right, done. So this is something about your rotor speed. Just 1 second. See Baba, his question just before I proceed further. Sir, if NR is 1500 and if NS is 1500 and NR is 1480, then the remaining 20 RPM will be considered as a loss or something else. See Baba, we talk about loss with respect to power, right? So the difference NS minus NR is to have a the TMF has to circulate a current, that current has to produce a power, and that power has to produce a torque, and the torque should make compensate that no load. So that's the reason that EMF should be there. For that there should be some relative speed. Please remember that, right? Done. Right. So what is the range of slip for an induction motor? It is 0 to 1. It cannot be equal to 0. Please confirm, all of you. Raise the hands if it is clear. Right. Done. Now just a link up. See, the rotor rotates in the same direction as the stator field. The rotor rotates in the same direction as the stator field with a speed nr which is less than ns, basing on the load. If there is no load on the motor, the speed will be, the rotor speed will be very closer to ns. If there is some load on the rotor, the speed will be little bit away. Why the speed has to depart, move means, as the load is increased, the motor torque has to increase. For more motor torque, the power has to increase. For power, rotor power, the current has to increase. For that, EMF has to increase. Further, the relative speed has to increase. Further, the rotor speed has to decrease. Like that, the rotor will adjust to the mechanical load. No load, the speed will be very close. With a load, the speed will be away from synchronous. Away means not far away. It is slightly away from synchronous. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. Done. Right. Now, see. Now, Silma is not over. Still pending. Now, at starting, as the rotor is steady, the relative speed between the stator field and the rotor conductors is ns. As a result, what is the frequency of the rotor currents? F. But you can see now the rotor starts rotating. When the rotor starts rotating, then obviously the relative speed between the field and the rotor conductors will start decreasing. When the relative speed starts decreasing, the frequency of the rotor currents will also start decreasing. Now let us see what will be the frequency of the rotor current during steady state, when the rotor has reached to its steady state. I can write, as the rotor starts rotating, rotor starts rotating, the relative speed between the stator field and the rotor conductors starts decreasing, and hence the frequency of induced EMFs in the rotor conductors decreases. Rotor conductors decreases, right? At steady state, what is that? At steady state, what is that? So F2 is equal to relative speed into poles by 120. Again, which field? Stator field. What with what speed it is rotating? Ns. What is the speed of the rotor? Nr into P by 120. So what I'll try to do means I'll divide with Ns and I'll multiply with Ns. So Ns minus Nr is nothing but S P into Ns by 120 is F. So what is the frequency of the rotor current means? It is SF. So can I write the frequency of rotor current at steady state means final rotation. Steady state is S into F. Is it clear? Confirm all of you. Is it clear? Confirm all of you. Raise the hands. Again, I repeat. So before we go for some advanced concept, please see, I'm giving a three-phase supply to the stator. Because of this three-phase supply, the three-phase currents are flowing in the three-phase winding in the stator core. And in that, those nature of poles are rotating. Right, internet problem. Right, just I'll disconnect and I'll connect. Right. Right. Now I think it is clear. Right. Now I come back. So whenever we are giving a three-phase supply to the stator, poles are formed in the stator core. As these poles are rotating, they are cutting the stationary. From my side, I don't think any issue. So you can see the screen is moving coolly, right? And these flux lines are cutting the rotor conductors. EMF is induced, and this EMF will circulate a current. The current carrying conductors placed under a magnetic field will experience a force. Because of this force, the rotor starts rotating, and in which direction the rotor will try to rotate means the rotor will try to rotate in the same direction as the stator field. With what speed it is rotating means it is rotating with a speed less than ns, that is nr. So who decides that less than nr means the load on the motor. If there is no load on the motor, the speed will be always closer to ns. When there is a load on the motor, the speed will be little bit moving away from ns. Why the speed will decrease with the increase in load means, so whenever the load is increased, the magnitude of opposition torque, load torque is increased. To compensate that, to make the rotor to continues to rotate, then this motor torque has to increase. For more motor torque, the rotor should have more power. For more power, the current should be more. For more current, the EMF should be more. For more EMF, the relative speed should be more. Further, the speed will try to decrease. Like that, the motor speed will try to decrease. But as the motor is not able to, or as the rotor is not able to catch the synchronous speed, we are finding out the difference and we are calling that one as a slip. Is this point clear? Is this point clear? Right. Now, as the rotor starts rotating, what happened to the frequencies of the rotor currents? The frequencies of the rotor current starts decreasing. At starting, the frequency is F, but during running, the frequency is reduced to SF, right? Now let us draw a line diagram. So with this line diagram, we are going to learn many things. Please see, this is a very, very important concept. Please try to learn. Line diagram, or it is a speed diagram. Line diagram. So using this line diagram, we can find out the relative speed concept, which is very important, and such questions will be asked in most of the interviews and exams also. I'm taking a reference here, and I'm representing that stator as a small rectangle. This one is a stator here, and those three-phase windings I'm representing like a three-phase circles or three circles. So represent three-phase windings, and whatever that excitation I'm giving, I'm representing like a lines, and those currents I'm calling it as IA, IB, IC. What are the frequencies of those currents? F. and for how many poles this stator is wound for p poles. Then when we pass a three-phase currents into those three-phase winding, immediately you can see the poles are formed. And what is the nature of those poles? What is the nature of those poles? Means with respect to stator, those poles are rotating with a speed of ns. Now I represent that speed with some line segment, some line, some line. So this is called a stator field. And with respect to stator, with respect to stator, with what speed it is rotating? ns. Let us consider it is moving in clockwise direction. So this length I'm using to represent the speed. Why? Because I cannot show the speed on the plain board, so I'm just representing that length as the speed. So with respect to stator, with what speed the field is rotating? It is rotating with a speed of ns. Let us assume that in clockwise direction. Is this point clear? Is this point clear? Right. So one thing. Right. Anyhow, we'll see. 1 second, wait. Right. Fine. Now, what is the speed of the stator field with respect to stator? Means, what is the speed? It is ns. Is this point clear? Right. Now, this field cuts which conductors? Stator conductors. When this field is cutting the stator conductors, what is induced? EMF. So, what is the frequency of that induced EMF? Means it is E1. And what is the frequency of that? F. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me. Right. Now this field is cutting the rotor conductors. What is induced in the rotor conductors? EMF. And as the rotor circuit is closed, that induced EMFs are circulating current, and the current carrying conductor placed under the magnetic field. So those conductors will experience a force, and due to that force, what happened to the rotor now? The rotor starts rotating. In which direction the rotor will start rotating? In the same direction as the field. Now we have assumed that the field is rotating in which direction? Clockwise. Even the rotor will also try to rotate in clockwise direction. Now let me draw that. Draw that. So again, I'm representing that rotor as a small rectangle. So with how many windings? 3 windings. So this one is the rotor. Here the rotor windings are close. So in which direction the rotor is also rotating? Clockwise. With what speed the rotor is rotating? NR. Then what is the frequency of the rotor currents during running conditions? SF. So if anyone questions you, or I am sitting on the stator here, you can see I'm sitting on the stator here. What is the speed of that stator field? Ns. What is the speed of that rotor? Nr. What is the speed of that stator field? Ns. What is the speed of that rotor? Nr. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. So tomorrow in your examination, if the questions are on this as of now, assume that the question will be like this. Assume that you are standing on the stator or you are sitting on the stator. So for you, what is the speed of the stator field? Ns. Right? For you, what is the speed of the rotor? Nr. For you, what is the speed of the stator? 0. Why? Because you are standing on the same stator and you are asking what is the speed of that stator. It is 0. Is it clear? Confirm me. Confirm me, all of you. Right. Now, before we proceed further, I'll just raise one question. After that, I'll give break. I'll come back. See, 2 points you note here. I'm having a stationary part, and in the stationary part stator, I'll be placing a 3-phase winding with a space angle of 120 degrees. Let the number of poles be P. Now, through this, I'm passing a 3-phase current IV, IC, the frequency of that current be F. Now, 2 questions I'll ask. What is the nature of that field? It is rotating. The nature of that field will be rotating. Is this point clear? Confirm me. Confirm me. Now, As the field is rotating, with what speed that field will be rotating? With a speed ns given by 120 into frequency by poles. So this is the speed at which this field will be rotating. Very good. Now what I will do means I'll take the same thing. Now this time to the same three-phase windings which are wound for p poles, I'm giving another excitation. I remove this with a frequency of xf. With a frequency of xf. If my question is there any rotating magnetic field with three-phase windings and three-phase current? Yes. What is the speed of that field? So it is nsx 120 into xf by p. Why? Because the frequency in this case is xf. It is xf by p. So it is x into 120 into f by p. So it is x into ns. So what is the speed of that field means? It will rotate with a speed x times of ns. Why? Because the frequency is xf, then the speed will be x times of ns compared to that ns. Is this point clear? Right. So once again I'm repeating. I'm having a stationary core. In that stationary core, I'm having a three-phase winding. I'm not bothered whether the core is rotating, dancing, sleeping, or jumping. I'm not bothered. So I'm having a core. In that core, there is a three-phase winding, and through that three-phase winding, I'm passing a three-phase current. Then we'll be having a rotating field. So with what speed that field will be rotating is, it is based on the poles which we are designing, the frequency of those currents which we are passing. It is 120 into f by p. If the poles are p, if the frequency is f, it will rotate with a speed 120 into f by p, right? But instead of that, if it is having a frequency of xf, then what is the speed at which that field will be rotating? It will be rotating with a speed of x into ns, x into ns, x into ns. Is it clear? Confirm me once again. Right. Now you please tell. For how many poles the stator is wound for? P poles. For how many poles the rotor is wound for? By default P poles. Otherwise there is no concept of motoring. So that is the reason if you look into the nameplate details, only the stator poles are given. Rotor poles are not given. It is understood stator poles and the rotor poles are same. Right. So I think people are interested for the break. I can see. Right. So I'll do one thing. So I'll go for the break. Right. After that I'll come back. Is it clear? All of you confirm me? Right. After that, I'll come back, please. Right. So I'm back. Right. Right. Confirm me, all of you. Raise the hands if you are able to follow me. Right. So now we are trying to talk about the relative speed. See, I'll continue. If a person is standing on the stator, what is the speed of the stator field means ns. What is the speed of the rotor means nr. Right. Now I'll continue. See, I'll be taking a stationary part. On the stationary part, you can see we have a three-phase winding. And each phase is wound for P poles. And through that, I'm passing a three-phase current. The frequency of each current is F. Then two questions I'm trying to raise. One is, what is the nature of that field rotating? Who decides the speed? Means it is the number of poles and the frequencies. If the supply frequency is say F, see one student asked, what is the meaning of X? See, if X is equal to 1 by 2, then what is the frequency? It is 25 hertz. Then what is the speed at which it will be rotating? 750. X is a scalar here, right? If F is the frequency and P are the poles, then what is the speed at which that field will be rotating? Ns, which is given by 120 into F by P. Please confirm me. Is it clear? Right. If the frequency is xf, where x is a scalar, right? If the frequency is xf, then what is the speed of that field? Means it is x times the supply frequency is the frequency, x times of the ns. So it is x into ns. So the speed at which that field will be rotating is x times of ns. Is it clear? Confirm. Is it clear? Confirm. Right. Now let me come back. Let me come back. Let me come back. So with respect to stator, how many windings are there? Three windings are there. What is the frequency of those currents which are passing through that F? Then what is the speed of that field? Speed of that field with respect to that winding? Ns. It is Ns. Similarly, in the rotor also, how many windings are there? Three windings. And each winding is wound for how many poles? P poles. And you can see three-phase currents. And what is the frequency of those three-phase currents? It is SF. Why? What is that S here? Slip. SF. Now, with the three-phase stator windings and three-phase stator currents with the frequencies of F, when it is producing a field which is rotating with a speed of ns, then these three-phase rotor conductors or rotor windings and these three-phase rotor currents with a frequency of S will produce as one more field which rotates with a speed of S into ns. Why S into ns? As the frequency of the rotor current is SF, then the speed of that field because of the three-phase windings and three-phase currents is S into ns. So with respect to rotor, with what speed that field will be rotating means it is S into ns. I call that field as rotor field. So can I give a statement like this? As the rotor also carries three-phase windings and three-phase induced currents whose frequencies are SF, then the speed of that rotor field with respect to rotor. Why? Because where is that current flowing? In the rotor circuit, conductors. So with respect to that rotor, with what speed that field will be rotating, the field will be rotating with a speed of S into ns. Simple, Baba. Stator have three-phase winding. The frequencies of those current is F. The speed is ns. The rotor is having three-phase winding and the frequencies of those currents is SF. What is the speed of that field? It is S into ns. When F gives ns speed with respect to that stator core, then SF will give S into ns with respect to rotor core. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. So can I give a statement here as The rotor also carries a three-phase windings and three-phase induced currents with a frequency of SF. The speed of rotor field with respect to rotor is S into ns. Why? Because the frequency is S, F, the speed of the field is S into ns. Is it clear? Confirm me, all of you. Is it clear? Right. I'll ask one question. See, I'm standing on stator. What is the speed of that stator field with respect to stator ns? What is the speed of rotor with respect to stator nr? What is the speed of that rotor field with respect to stator? No idea. I have only the speed of the rotor field with respect to rotor is SNS, but the speed of the rotor field with respect to stator, I don't know. Is this point clear? Confirm me, all of you. So can I write like this? The speed of the next point, the speed of the rotor field. You can see how many fields are present now? Two fields. Rotor field with respect to rotor is S into ns, where S is the slip. So now there are two fields in the area. One field is due to the stator winding and supply current. With respect to stator, it is rotating with a speed of ns. The other one is due to the rotor windings and induced currents. With respect to rotor, in the same direction, it is rotating with a speed of S into ns. There are two fields. One is with respect to stator, which is rotating with a speed of ns. The other one is with respect to rotor, it is rotating with a speed of S into ns, right? I hope it is clear. Now I'll ask one question. Get ready for the answers. Let me see how many will answer. Please try to answer it. Get ready with the answers. See, I'm standing on center of a railway track. I'm having a railway track. And let us consider that I'm standing on the center of a railway track. So on the track, there is one train standing, and in that there is one person sitting. One person is sitting in the train. The train is standing and that person is sitting in the train. If my question is, what is the speed of that person with respect to me? I'm stationary, I'm standing, train is standing, that person is sitting in the train. What is the speed of that person with respect to me? What is the answer? 0. Excellent. The answer is 0. Excellent. 0. Why 0? I'm stationary, I'm standing, and the train is standing, and the person is sitting in that train. The speed is 0. Excellent. The speed of that person with respect to me is 0. Excellent. Right? Excellent. Then say the train is moving now, moving with 5 kilometers per hour, right? And that person is still sitting in the train, right? What is the speed of that person with respect to me? The train is moving with 5 kilometers and that person is still sitting in the train. Then what is the speed of that person with respect to me? Can you please tell me? Answer. 5 kilometers, right? See, I'm talking about the speed. Don't say minus or plus. What is the speed? 5 kilometers per hour. In other way, if I want to catch that person, so with what speed I have to run? I have to run with a speed of 5 kilometers per hour so that I can catch that person. Is it clear? Is it clear? All of you raise the hands. Right. Now what happened is that person has stood up, he stands in the train and he walk in the train with 1 kilometer per hour with respect to moving train. So with respect to train, with what speed he is moving? 1 kilometer per hour. 1 kilometer per hour. then what is the speed of that person with respect to me? If I want to catch that person, with what speed I need to run now? I want to catch that person, with what speed I need to run now? Can you please tell me? Yes, it is 6. It is not 4. It is 6. Yes, not 4, Baba. It is 6. Why? Because if I want to catch that person, first I need to run with the speed of the train 5 kilometers per hour. Then I need to run with the speed of that person with respect to train 1 kilometer. So it is 6 kilometers per hour. So if I want to catch that person, I need to run with 6 kilometers per hour. Please confirm me. All of you raise the hands. Raise the hands. Yes. I'm not talking about any aptitude here. Just it is required. Now you please tell me. You please tell me. So with respect to the stationary observer, what is the speed of the rotor? It is nr. And with respect to rotor, what is the speed of the field? S into ns. Then what will be the speed of that rotor field with respect to the stator? Means it is the speed of that rotor field with respect to rotor, and the speed of the rotor with respect to stator. It is something like, I'm calling myself as a stationary person who is standing at the center, and the rotor is the train, and in that the person is the rotor field. So if I want to calculate the speed of the rotor field with respect to me, so the speed of the rotor field with respect to rotor and the speed of the rotor with respect to reference, then it is the total speed. Is this point clear? Confirming. Is this point clear? Confirming. Once again, I'm repeating. There are two fields. One field is with respect to stator, it is rotating with ns. The other field with respect to rotor is rotating with the speed s into ns. Now I need to find out what is the speed of the rotor field with respect to stator. So it is the sum of the rotor field with respect to rotor and the rotor with respect to stator. Yes, Imtiaz Pasha, very good. NR plus S into NS. Very good, Baba, right? Done. So can I write like this? The speed of rotor field with respect to stator is sum of rotor field with respect to rotor and a rotor speed with respect to stator. So what is the speed of the rotor field with respect to rotor? S into ns. What is the speed of the rotor with respect to stator? Nr. So it is, you know that yes, I can write it as ns minus nr by ns into ns plus nr. So here ns will get cancelled, nr will get cancelled. So here even the rotor field is also rotating with the speed of ns. So here can I say this rotor field with respect to stator is ns. So the rotor field with respect to stator is ns. Then you can see already in the stator core, the stator poles are rotating with the speed of ns. Now even the rotor poles also with respect to the same stator, they are rotating with the speed of ns. Then what is the relative speed between these two poles? The stator poles and the rotor poles with respect to a common reference stator. The stator poles are rotating with ns. The rotor poles are also rotating with the speed of ns. What is the relative speed between these two fields? 0. As the relative speed between the two fields is 0, stator poles and the rotor poles are stationary with respect to each other. When they are stationary with respect to each other, there is a continuous attraction and repulsion. Because of that, there is a continuous rotation. Like this, the rotor will continue to rotate. I hope this point is clear. All of you confirm me? Confirm me? Yes. So very good. Jai Krishna. Right? Pratyush. The relative speed is 0. Very good. Jai Krishna. Very good. The relative speed is 0. So the relative speed between the stator field and the rotor field is 0. Once again, as the rotor carries a 3-phase windings and 3-phase current, because of the 3-phase windings and 3-phase current, we have one more field, one more pole pair, which is rotating in the rotor core with a speed of S into ns. With respect to rotor, it is rotating with a speed S into ns. Then with respect to stator, with what speed that poles will be rotating is S into ns plus nr. It is nothing but ns. Already the stator poles are rotating with ns. The rotor poles now with respect to stator, they are rotating with the speed of ns. What is the relative speed between these two? 0. That means the stator field, the rotor field are having a relative speed of 0. Please note here, this one is the rotor. Rotor is not rotating with ns. Rotor is always rotating with the speed less than ns. So our concept is the relative speed between the fields. So the stator is stationary, the poles are rotating with ns. With respect to rotor, the poles are rotating with sns. But with respect to rotor, the rotor poles are rotating with ns. The relative speed between these two fields is 0. 0. So if my question is like this, I am standing on stator. What is the speed of the stator pole? Ns. What is the speed of the rotor? Nr. What is the speed of the rotor field? Ns. Once again, I am standing on the stator. What is the speed of the stator field? Ns. Rotor? Nr. Rotor field? Ns. Is it clear? Confirm me, all of you. Right. So can I write like this? Therefore, 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 the speed of a rotor field. So this is also rotating. Rotor field with respect to stator is ns. Ns. As the stator poles are filled, both are same, poles are already rotating with ns. The relative speed between the two fields is 0. Hence stator poles and rotor poles are stationary with respect to each other, and hence the relative speed, and hence due to continuous attraction and repulsion, the rotor rotates. Rotor rotates. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me. Right? See, Baba, it is not the question of magnetic locking. See, what is the meaning of magnetic locking means the two poles should get locked, right? So, and these two should rotate, but it is not the question of locking. It is something like the poles are chasing. So the rotor is chasing. So it is something like following. There is no question of locking. 1 second. So I'll just put the charging. It is 8%. 1 second, I'll put charging. Right. So is it clear? I'll confirm with me. Is it clear? Is it clear? I have to raise the hands. Right. Done. But still, your concept is not over. So it is the interaction between the two fields. If you go back to your DC motor, So I think day 5, I don't know, day 5, yeah. Then you can see here how the DC motor rotates. Already we have seen before to the day 4, I think. So day 5, where is day 4? Yeah, day 4. So if you remember DC motor, I told you that, see, the basic property of the magnetic flux lines is to take the straight path. But whenever we are supplying current through that armature conductor, there is one field. Because of that, they are forced to take the longest path. Because of that, there is a force acting on the armature conductors, and hence the armature will try to rotate. This was already explained to you in my previous class. Is this point clear? Confirm me. So here also let me explain what is the mechanism. See, I'm giving a three-phase excitation to stator. See, I'm trying to explain all the concepts. I'm not leaving anything pending. Please remember. So whenever a three-phase supply is given to the stator winding, what are formed in the stator core? Magnetic poles. So whenever we are having magnetic poles, you can see we are having magnetic flux lines. Magnetic flux lines. And here you can see the rotor conductors. When the poles are stationary, if I assume, when the poles are stationary, if I assume, those magnetic flux lines will be going straight. They are taking the least reluctance path straight. But what is the nature of these poles? So this I call it as the stator field. With what speed this stator field is rotating? Ns. As this pole starts rotating, then those flux lines will cut the rotor conductors. When they are cutting the rotor conductors, what is induced? An EMF is induced. Because of that EMF, there is one more flux in the area like this. That we called it as rotor field, which is rotating with the speed of ns. But now you can see this conductor is coming along this path. As a result, what happened to these flux lines? These flux lines will try to take this path. Take this path. Why they are taking the longest path means because of the current which is induced, because of the flux which is produced, they are taking the longest path. Now the stator flux lines will say, no, 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 no. You are making us to take the longest path. No, 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 no. Please move from this position. So these are the resultant flux lines. So these resultant flux lines are making the rotor to move. Why? Because they are bending, but they are supposed to come to straight path. To come to the straight path, they will be exerting a force on the rotor conductors, and hence this rotor will try to rotate. So please remember that the stator field alone, the rotor field alone is not producing any torque. The interaction of, that means when these rotor field lines are coming on the way to the stator field line, there is a resultant which is making the flux lines to take the longest path. So due to this resultant, this is making this force. So why? Because they want to take the straight path. When they want to take the straight path, they're making, please move. So this rotor conductor will move, and hence the rotor will continue to rotate. So these we call it as the resultant field. So if anyone questions you, are because of the individual field, the rotor will rotate, or it is due to the interaction or the resultant of two fields, the rotor will rotate. Two fields. Only one field will not produce a rotor to rotate. Now I'll explain the mechanism. See, rotor is initially sleeping. When you are giving a three-phase supply, flux lines are formed. These flux lines, they cut the rotor conductors. What is induced? EMF. Because of that EMF current, because of that current, there is one more flux. This flux is making the main flux to take the longest path. So for that, there is a force exerted like this. The rotor conductors will try to rotate. So it is a resultant force which is responsible, or it is the individual field. It is a resultant field which is making the rotor to rotate. So at steady state, which flux will make the rotor to rotate means the resultant field. So the resultant field is the sum of stator field and the rotor field. Resultant field is the sum of stator field and the rotor field. It is not like ns plus ns to ns. It is the resultant of these two fields. So finally, what is the equation for EMFs? So E1 is equal to 4.44 F phi R N1 kW1, and E2 is equal to 4.44 F2 phi R N2 kW2. So here F2 is equal to SF. Is this point clear? So which field is making the rotor to rotate means the resultant field. So that resultant field will also rotate with the speed equal to ns. So if anyone questions you, are finally, how many fields are there in the air gap means only one field. So which field is responsible for making the rotor to chase means the resultant field. So initially stator field, rotor field, interaction, resultant, and this resultant is making the rotor to rotate. So finally the resultant will make the rotor to rotate. I hope this point is clear. All of you confirm with me? Raise the hands. Right. So this is something about your operation of an induction motor, but still some concept is still pending. I'll come back. So if anyone asks relative speeds concept, relative speed. So please get ready with the answers. Please try to answer. I'm standing. So one question, Ramakrishna Repalli. Sir, why fields and poles are equal? Are Baba? Because of poles only the magnetic field is produced. See, if anyone talk, this is a pole, then this is only producing a field. Field and poles, I mean to say both exchangeable I can use. I can use sometimes the relative speed between the poles. I can use sometimes the relative speed between the fields. Ramkrishna Repalla. Is it clear, ma? Ramkrishna. Is it clear? Right. Okay, Baba. Right. Now last. I'm standing on a stator. What is the speed of that stator field with respect to me? Answer. Yes, excellent. NS. Excellent. NS. Very good. NS. Right. Now, what is the speed of rotor with respect to me? Rotor with respect to me. NR. NR. Excellent. What is the speed of the rotor field with respect to me? Speed of the rotor field with respect to me. Rotor field. NS. Excellent. Excellent. What is the relative speed between the two fields? It is 0. The relative speed between the stator field and the rotor field is how much? Please answer. The relative speed between the stator field and the rotor field is how much? 0. Right? It is enough. I'll give the same points. Don't answer enough. Observations 1. So before do that, I'll ask one question. What is the role of back EMF? No textbook will explain this. Role of back EMF. Back EMF. That is E1. E1. What is the role of back EMF? E1. Can anyone tell? Can anyone tell? I'm waiting. Anyone can tell? Role of back EMF. So answer for this. Role of back EMF. Starting current reduction, opposition to supply, circulating current in windings, to balance limiting current, to produce rotor flux, conversion, feedback, for production of continuous torque. Motoring is done because of back EMF, correct? For power transfer, correct? Power balance, as you said, correct? Yes. Anyhow, I'll explain. Please, enough. It is enough. I'll explain. See. Before I try to explain the concept of back EMF for motors, I'll take a transformer. If you are clear with this, I can come back here. Please see. So here, I'll be taking a transformer, which already I explained to you. So this will be having primary windings. If I give the excitation, I can name it as primary and secondary. So whenever I give some excitation to this, so this primary will draw a magnetizing current. Because of this magnetizing current into N1 will produces one MMF. This MMF will produce as a E1 or flux. As the nature of that flux is varying, then it will induce as a EMF in both the windings. Now, how many fields are present in that? Only one field. Which field it is? The phi m. There is no concept of power transfer here. There is no power transfer. Absolutely no power transfer. Why? Because there is no secondary field. Secondary field. Now, if I connect a load, then what circulates through this current? This current into this secondary turns will produce one more flux. This flux will oppose the main field flux. As a result, this main field flux will decrease. The EMF induced in the primary will decrease. Then I1 is equal to V minus E1 by Z1. When E1 decreases, this difference will increase. The current drawn will increase. When current drawn increase, V into I1, the power drawn will increase. And where is that power going? Where is that power going? Means that power is going to the load, right? So how that load is communicating, how that load is communicating to the primary to draw power means. So whenever we connect a load, so a current circulate. Because of this current, there is one flux. This flux will start opposing the main flux. The flux in the core will decrease, EMF will decrease, V minus E1 will increase, current drawn will increase, power drawn will increase, and hence that power is fed to that load. Is this point clear? Confirm me. Confirm me. Right? So the same manner here also, I1 is equal to V minus E1 by Z1, and here E1 is equal to 4.44 F phi R N1 into KW1. Now let us consider the motor is running without load. Freely rotor is rotating without load. The motor is freely rotating without any load. Right? Now please tell me, whenever I am increasing the load, mechanical load, what happened to the speed? Decreases. When the speed decreases, the relative speed between field and conductors will increase. When the relative speed increases, the flux will increase. When the flux cuttings increases, the EMF, what happened? Right, wait. I can understand. All of you raised the hand. Wait, I'll come back. Don't worry. Now, is it clear? Confirm, all of you raise the hands. Is it clear? Is it clear? Right. Now, now please see before I proceed. Now, if I increase the load again here, what happened to the effective resistance of the load? Decreases. The current increases, the flux phi2 will increase, the position to the main field will increase, the flux in the core decreases, E1 will still decreases, B minus E1 will increase, current drawn will increase, power drawn will increase, that power is fed to the load, right? So like that, with the variations in the load, the current is varying. With current, phi2 magnitude is varying. With phi2, opposition is varying. With opposition, E1 is changing. With E1, V minus E1 is changing. With V minus E1, current drawn is changing, power drawn is changing, and that power is going to the load. Is it clear? Is it clear? Confirm me. So if there is no back EMF in transformers, then there is no concept of power balance. 100% there is no concept of power balance. There is no concept of power balance. So that EMF is playing a key role in balancing the power. Similarly here, say the induction motor is running without load. When the induction motor is running without load, then the rotor speed will be very closer to ns. When the rotor speed is very closer to ns, the relative speed is very less. The flux cuttings will be less. The currents will be almost less. When the rotor currents are almost zero, the rotor field will be almost zero. Then opposition to the main field is very, very less. The change in phi r will be very, very less. As change in phi r is very less, the change in E1 will be very, very less. Current drawn will be very, very less. Power drawn will be very, very less. And that power is fed only for compensating the losses in the machine, not for producing the mechanical power. Is this clear? Is this clear? Right. Now see, when I'm increasing the load, what happened to the rotor speed? Decreases. The relative speed increases. Flux cutting the rotor conductors increases. EMF increases. Rotor current increases. Phi 2 increases. Opposition increases. Phi R decreases. E1 decreases. V minus E1 by Z1 increases. The current drawn increases. The power drawn increases. Power fed to rotor increases. The torque increases to compensate the load. So what is the mechanism? I'm increasing the load. When I'm increasing the load, how the input will know that in order to compensate that load, it has to draw more power. Why? Because load is a mechanical parameter. This power drawn is an electrical parameter. How there is a communication means whenever you're increasing the load, the speed decreases. When speed decreases, relative speed increases, flux cuttings increases, current increases, rotor flux phi 2 magnitude will increase, opposition to the main field will increase, flux in the air gap will decrease, E1 will decrease, stator voltage, E1 will decrease, V minus E1 will increase, current drawn will increase, power drawn will increase, power fed to the rotor will increase. As power coming to the rotor is increased, the torque will increase, and this will supply the load, and as the motor will continues to rotate. Is this point clear? Confirm all of you. Is this point clear? Right. So who is finally balancing the power means even. When there is no even, there is no concept of power balance. I hope this is clear. All of you finally conclude. Raise the hands. Raise the hands once. Right. I'll write some observations. Please go through some observations. Some observations. Some observations. First, the speed of just I'm giving one, you can calculate anything. The speed of stator field with respect to A, stator structure is ns. B, rotor structure is s into ns. That is ns minus nr. How can you say? See here. I want to find out the speed of stator field with respect to rotor. Stator field is rotating with ns, rotor is rotating with a speed of nr. What is the relative speed between this? Ns minus nr. Then C, the rotor field is 0, right? I hope this point is clear. All of you confirm? All of you confirm? Only few. What about others? I need the answers from all. Right. The second point, which was asked many times in the examination, C, the phase sequence of the three-phase supply is ABC. The field is rotating clockwise. The rotor is also rotating clockwise direction. Now for say, if I change the phase sequence of the stator field, a stator excitation, then what will be the frequency of induced EMF at that instant? What do you mean by that? See here, all of you. So initially I'm having a stator. And what is the phase sequence of the three-phase excitation? ABC. Let me consider ABC. ABC. What is the frequency? F. How many poles? P. What is the speed of the stator field? It is ns. Then in which direction the rotor will also rotate? In the same direction. With what speed the rotor will rotate? nr. What is the frequency of the rotor currents? sf. Why? Because the relative speed is ns minus nr. The frequency is sf. Now what I have done is during this running condition, I have changed the currents in two phases. When I have changed the currents in two phases, so here I'm supplying IC and I'm supplying IB. When I'm changing the currents in two phases, very immediately, what happened to the direction of the field? Reverse. So the stator field doesn't have any inertia. The stator field doesn't have inertia. When the phase sequence is ABC, say the field direction is clockwise. When the phase sequence is ACB, the direction of the field will be counterclockwise. Then this field will be immediately moved to this direction, immediately. Then what will be the frequency of induced EMFs in the rotor winding at the instant of changing the phase sequence? So this will not be SF. So what will be the frequency? Then you know that the frequency is nothing but the relative speed. So you can see this case, this field is rotating with ns in counterclockwise. At that instant of changing the phase sequence, this is rotating with a speed of nr in clockwise. So what is the speed? Ns plus nr into p by 120, right? So I take this ns plus nr, I will add one ns and I'll subtract one ns. So ns plus ns is how much? 2ns, and I'll take minus common, ns minus nr here. So I'll divide numerator and denominator with ns. If I divide, then I'll get 2 ns minus nr by ns is f, right? So not like that, just wait. So what I'll do means, so can I write this one as 2 minus 2ns minus nr by ns. So I'll substitute the same thing here. Same thing here. This I'll substitute here. That is 2ns minus ns minus nr into p by 120. I'll divide with ns here and I'll divide with ns here, right? I can do that. Is this point clear? Is this point clear? Confirm me. Then if I simplify this, 2ns by ns is 2, ns minus nr by ns is f, p into ns by 120 is f. What is the frequency of the rotor EMF? It's 2 minus f, 2 minus s here, 2 minus s into f. So this is a very, very important question. Many times there is a question asked on this. What is that? Say the phase sequence of a three-phase induction motor is ABC. ABC. Then the rotor is rotating in the same direction as the field. Then if the phase sequence of the stator excitation is changed, if the phase sequence is changed, then what will be the frequency of induced EMFs in the rotor conductors, right? Right, what happened? You're raising the hands. Is it clear? My voice is clear. All of you raise the hands. My voice is clear. See, but those who have raised the hands is not from my side. Why? Because majority of the student has raised the hands. See, the problem may be from my side or from your side. If it is from my side, I'm trying to rectify. Why? Because maximum students are raising the hands, but I can see only 4 or 5 people are raising the hands. You please try to understand that, right? Please, anyhow, I'll repeat. See, initially, the rotor is rotating in which direction? Say clockwise. Why? Because the direction of the field is clockwise. What is the relative speed between the field and the rotor conductors? Ns minus Nr. Then the frequency is SF. Then what I have done is, I have changed the stator phase sequence. When I have changed the stator phase sequence, immediately what happened to the direction of the field? Reverse. When the direction of the field reverse, then the relative speed between the stator field and the rotor conductors will be changed. So it is direction, but due to the inertia, the rotor will be rotating in the same direction. 1 second, I'll come back. I can understand. I'll come back. Just right. right? So fine. So I think it is clear. Just I told if anyone is using the net to switch off, right? No one is using anyhow, but we are back. So is it clear? Now please raise the hands. Is it clear? Just if any my dad is anyone is using, just I told them to switch off, but no one is using, right? Anyhow, I'm back now. So this is something about the frequency. Now the question is, see if the phase sequence is ABC, in which direction the field is rotating clockwise, in which direction the rotor is also rotating clockwise. What is the relative speed between those two, ns minus nr? But when I'm changing the stator phase sequence, then immediately what happened to the direction of the field? Reverse. When the direction of the field reverse, the relative speed between the stator field and the rotor will be ns plus nr. Ns plus nr. Then what will be the frequency of the rotor currents at that instant of time? Means it is 2 minus s into f. 2 minus s into f, that at that instant. Is this point clear? Confirm me. Is it clear? Confirm me. Right, very good. So can I write a note? If the stator phase sequence is changed, then the frequency of induced EMFs in the rotor conductors at that instant is 2 minus s into f. Is it clear? Confirm me all of you. 2 minus s into f. Is it clear? Confirm me all of you. Right. So this is something about your so-called as the second point. I'll give an example. Now let me work out an example on that. Please see. All of you get ready. Please try to answer this. A numerical. The full load speed of a three-phase 50 hertz induction motor is 285 rpm. 285 rpm. For this motor, find one, number of poles, two, the speed of stator field, SF means stator field, with respect to one, stator, two, rotor, C, a rotor field. I hope this point is clear. Now let us find out. So here, what is the rotor speed given? Rotor speed at full load. Our rotor speed is given as 285 rpm. So we don't have any poles, right? Now I need to find out the number of poles. How to find out the number of poles? Let us see. So here I'll prepare a table. What is that? For 50 hertz supply, one side I take poles, on the other side I'll take ns. Ns is equal to 120 into f by p rpm. So what are the minimum poles we'll be having? 2. For 2, it is 3000. For 4, 1500. For 6, 1000. Like that, if I calculate for 20, 300. For 24, right? Like this, if I find out, we'll have 250. Like this, we'll have. Now, you know that the rotor speed will be always closer to synchronous speed. And that synchronous speed should be more than that. So what is the synchronous speed closer to 285 and more? It is 300. So definitely for 300 and for 50 hertz, the machine should have how many poles? 20 poles for sure. So it is assumed that if the machine is having 20 poles, for the 20 poles and 50 hertz, the synchronous speed will be 300. As the synchronous speed is 300, the rotor speed is closer to 300, 285 RPM. So it is reverse engineering. So the rotor speed is 285 RPM now. Then for 50 hertz, what will be the synchronous speed closer to this 300? Then for 300, how many poles the machine should have? 20 poles. You can see 20 poles are here. Is it clear? Confirm me. Is it clear? Confirm me. So can I write the synchronous speed closer to 285 RPM is 300 RPM. Therefore, for 300 RPM, Ns is equal to 300 RPM and F is equal to 50 Hertz. The machine poles should be 20. The machine should have 20 poles. Now, whenever a relative speed concept is asked, then you draw these three lines. What are those three lines? This one is a stator. With respect to stator, the stator field will rotate with Ns. What is the case of Ns here? 300. And this rotor is rotating with a speed of 285 RPM. And this rotor field is rotating with a speed of 300 RPM. Now the question is, what is the speed of the stator field with respect to stator? It is 300 RPM. The speed of the stator field with respect to rotor, 300 minus 285, it is 15 RPM. The speed of the stator field with respect to rotor field, it is 0. Like that you can find out. Is this point clear? Confirm me, all of you. Is this point clear? Right, done. So this is something about the so-called as the numerical. Is this point clear? Confirm me, all of you. Is it point clear? Is this point clear? Confirm me, all of you. Right. So this concept, this complete the concept of working principle or the concept of rotor rotation. So if I once again repeat, so what are the laws we have used? Faraday's law, Fleming's right hand rule, Fleming's left hand rule, Lenz's law. But what is the law which is governing the motoring means the Lorentz law. That is, the current carrying conductor should place under a magnetic field. Due to that, the rotor has to rotate. The first condition B is due to the three-phase windings and three-phase current, the conductors are the rotor conductors and the currents are induced current. Like that, we have seen with respect to Lorentz law. Is this point clear? Right. And the second one is the relative speed between the two fields should be 0. The stator field is rotating with the speed of ns with respect to stator. The rotor field with respect to rotor, it is sns. With respect to stator, it is ns. The relative speed between these two fields will be 0. And one more point to be noted carefully is, in the coming days, if you are coming across this frequency, which frequency 2 minus s into f. So this frequency is a dangerous component. Why? Because the field is rotating in one direction, the rotor is rotating in opposite direction. That the relative speed between these two is too large. If the relative speed is too large, the flux cuttings will be more, EMFs in the rotor conductors will be more, currents will be more, ohmic losses will be more, the temperatures will be very high, and the windings will get damaged. If this is only for short time, no problem. But if this is existing for long time, the windings will get damaged. But in this case, what happened is, so here initially the field is in this direction. The rotor is seeing that field and rotating. But when as the field direction is reversed, then the rotor will slow down. Why? Because according to Lenz's law, the relative speed has to be reduced. So the rotor will slow down in clockwise direction. It comes to rest and it will rotate in counterclockwise direction and try to catch the field in counterclockwise direction. So it will take some time. So it will come back to that again counterclockwise direction. It will not be like rotating with the same n in clockwise direction. It will come back to counterclockwise direction also to obey Lenz's law. Is it clear? Confirm? Is it clear? Right. So this is something about your so-called as the working principle, right? Now let us go for some question and answers. Why? Because this is a key area where we need to spend some time, right? We'll see. Right, done. So See, rotor poles cannot be 19, Baba. See, poles will always exist in even number. 19 cannot be like, right? So it should be either 20 or 18. 18 cannot be. So it is only 20. Please try to make that point. Right. So I'll come back. Just give me time. I'll bring that earphones. Right. Thank you. Right. Let me see. Right. Fine. Right. I'll go back to this question and answers, raising the hands. Just see, my sincere request, my humble request, my kind request. Please, you ask n number of questions from the content concepts which we have discussed today. I have absolutely no issue. But for God's sake, don't ask the questions from the topics which we are going to cover in the coming days. I can tell absolutely I have no issue. But it is something like the other people may feel bored. So please ask the questions from the concepts from this. And here I'll explain. Please try to understand that. Right. First.
Sir,
Yeah.
sir, we discussed that.
Yeah, you raise Muthu Reddy.
Sir, if we use supply to the rotor and then stator is short circuited, can we
See that?
expect the?
Yeah, very good question, but that I'll be discussing in the coming days. So that we call it as inverted induction motor operation. Inverted means instead of giving a three-phase supply to the stator, if the excitation is given to the rotor with the stator winding short circuited, then in that case, the rotor will rotate in a direction opposite to the rotor phase. Why? We'll see that. Okay. But as of now, for your question, the answer is the rotor will rotate in a direction opposite to the stator field, again to obey the Lenz's law there. Understood, Reddy? I'll explain that. Right? Any question from this today's class still?
No, sir.
Right. Thank you. Right. Anil.
Sir, hello, sir. Good evening, sir.
Baba. Good evening.
Sir, we have said in last observations.
Yeah. Last observation.
Yes, sir. In that second point, I don't understand clearly.
See, if the phase sequence is reverse,
Okay, sir.
if the phase sequence is changed, what is the initial phase sequence? ABC, right?
Yes, sir.
If I change it to ACB, what will be the direction of the field?
Definitely opposite to the normal position. Horizontal.
Yeah. So, but due to the inertia at that moment, in which direction the rotor will be rotating? The previous direction. That is clockwise, right?
Yes, sir.
Due to inertia. So, for that instant, it will rotating clockwise direction, correct?
Yes, sir.
Then what is the relative speed between these two now? What is the relative speed? So, one field is rotating. This is rotating in opposite direction. What is the relative ns plus nr, correct?
NS plus NR. Yes.
If I simplify that, then what will be the frequency we are turning to be? 2 minus s into f, right? So whenever I'm talking about 2 minus s, those frequency components are dangerous component. Is it clear, Anil, now?
Yes, sir. Instead of P by 120, here we will write NS minus NS. What is that, sir?
See, it is not ns minus ns. See, it is relative speed into poles by 120 to calculate frequency, correct?
Yes, sir.
So what is the relative speed now?
NS plus NR.
Then that ns plus nr, I can write it as 2ns minus ns minus nr. Can I write?
Okay, sir. Okay, sir. Understood.
Right. Okay. Right, Babu.
Okay,
Right. Right. Bhavani. Sai Charan Reddy, I need. Where is he? Right. Dupati Bhavani. Bhavani, you are there? Hello? Bhavani. No. Right. Pratyush.
Hello, sir.
Ha, Baba, please ask.
Sir, sir, I have a doubt regarding yesterday's class, sir.
Yeah, you can ask. Yesterday's class,
Sir,
no issue.
yeah, sir. In case of air gap of squirrel cage induction motor, you have said that that is having less air gap. So,
Smaller
due to less magnetizing current, it has good power factor, no, sir.
during running, correct.
Yes, sir. For in and you have said that in case of rotor, it is having as it is having low resistance. You have said that it is having poor power factor.
That is at
Sir,
starting.
sir, means that cos theta 2 can be treated as a secondary power factor, sir.
Yes. Whatever the thing I have given, it is a primary power factor. Both are not same.
Due to air gap, that is primary power factor, sir.
Correct.
Okay,
Understood.
sir. Yes, sir.
Yeah.
Sir, and that doubt, sir. Sir, you have said that F is equal to relative speed into P by 120, no, sir.
Yes.
Sir, is that valid for in synchronous machines also, sir?
Obviously, it is a general.
Okay, sir. And that can be valid in case of running conditions also, sir.
Yes. Wherever you want, you can go. See, in case of synchronous generator, I want to find out the frequency of the EMFs in the stator winding, right?
Yes, sir.
What is the speed of the rotor field with respect to stator? It is N. How many poles?
Yes, sir.
P by 120. Then the same one you will get. Understood? Pn by
Yes, sir.
120. Right? It is same. Understood, Anil?
Okay, sir.
Right.
Yes.
Sorry,
Yes,
Pratyush.
sir. Thank you.
Right.
Yes. Thank you, sir.
Right. See, no one is raising the hands today. Why? Because hope see, I can see. People are raising now. Okay. Bhaskar.
Hello, sir.
Ha, Baba.
Sir, when the phase sequence is reversed, how the rotor will rotate in opposite direction, sir?
I never said rotor. See, you try to mute there. I'm just reflecting my voice. Now you are clear, Bhaskar. Bhaskar.
Yes, sir.
Yeah. See, I never said the rotor will rotate that instant, but whenever you are changing the phase sequence, what will be the direction of the field at that instant? Reverse. Correct?
Yes.
Why? Because this was already been proved in rotating magnetic field. When the phase sequence is reversed or changing the currents in two phases is changed, then the direction of the field will be reversed. But due to inertia at that instant, in which direction the rotor will be rotating? Clockwise. Then what is the relative speed between these two? Ns plus Nr. Bhaskar.
Yes, sir.
Understood?
Yes, sir. But after some time, it will rotate in opposite direction.
Why? Because to reduce the relative speed, the Lenz's law says that so the field is moving in counterclockwise direction. To reduce the speed, relative speed, in which direction the rotor has to rotate? Same counterclockwise. But unlike your field, immediately it will not come back. So it will slow down, decelerate in clockwise direction, come to zero, then it will rotate in clockwise direction. It will take some time. Understood?
Okay, sir.
Right.
Sir?
Yeah, please.
Sir, in transformer, you are saying that opposing flux will oppose the main flux and the flux will reduce.
Yes, it is
So
at
it
that
is a constant flux device, no, sir?
See, of course, it is a constant flux device, but there is a slight change in the flux. That means even a small change in the flux, there is a large change in the current. It is something like this. You are having 100 rupees. You lost something like 50 paisa somewhere. Then I say you are having 100 rupees or I say it is only 99 rupees something. So can I make it 100 rupees?
Okay.
Bhaskar.
Okay, sir.
Understood. There is a small change in flux, which is the ignored concept. Without change in small flux, there is no change in even there is no change in current, there is no change in power transfer. A small change, 0.01% will also make large current to draw. So a small change in current, but we ignore that change and we call it as a constant flux. Bhaskar. Understood?
Okay, sir.
Right. Right. Vikrant.
Good evening, sir.
Good evening, Vikrant.
Sir, doubt is on initially the speed of stator field with respect to rotor field is we assume that it is ns.
Initially, no. How can be it is ns? Initially, at starting, you mean to say?
Yes, sir.
At starting, what is the frequency of the rotor currents? What is
To
the
be,
supply frequency?
yes, sir.
Then what is the relative speed between those two? It is 0 only. So when the rotor speed is increasing, the rotor frequencies are decreasing, the speed of the rotor field with respect to rotor is decreasing, but the relative speed between these two is maintained 0 every time.
Okay, sir.
Understood, Vikrant?
Yes, sir.
Right. Still any question more?
Nothing, sir.
Right. Ajay.
Good evening, sir.
Good evening, Ajay. Yeah, please, Ajay.
Sir, vacuum ఒకసారి explain చేయవలసిన కాన్సెప్ట్.
ఇప్పుడు whenever you just reduce, whenever the load is increased, what happened to the speed?
Decrease.
Relative speed?
Decrease.
Increase.
Increase.
Flux cuttings?
Increase.
Rotor currents?
Increase.
Rotor flux?
Increase.
Opposition to the main field?
Increase.
Flux in the air gap?
Increase.
Decreases. Opposition between the flux. What happened to flux in the air gap? Decreases.
Increase. Yes, sir.
Then E1
E1
decreases.
Yes, sir.
V minus E1
E minus increase.
Then current drawn,
Increase.
power drawn,
Increase.
power fed to the rotor,
Increase.
torque
Increase.
increases. To compensate which torque? Load torque. Understood, Ajay?
Yes, sir.
Right. Still any doubt?
సార్ ఇంకొకటి అంటే మీరు టార్క్ మొత్తం రిలేషన్ రాసింది కదా సార్, ఫ్లక్స్ ఇంక్రీజ్ డిక్రీజ్,
రాశాను కదా.
అది ఒకసారి ఎక్స్ప్లెయిన్ సార్.
అదే
ప్రాబ్లం.
అదే కదా చెప్పింది. ఇప్పుడు లోడ్ పెంచాను, వాట్ హ్యాపెన్ టు స్పీడ్? ద సేమ్ థింగ్. రిలేటివ్ స్పీడ్.
ఎస్ సార్, ఎస్ సార్,
అండర్స్టూడ్ నాన్న. రైట్ నాన్న. రైట్
థ్యాంక్ యూ.
రైట్. Right. Anil Kumar. This is another. Good evening. Another Anil Kumar, I think. Yeah, Anil.
Sir, could you please explain that rotor field frequencies are NS?
I didn't get you. What do you want? Rotor frequency?
Yes, sir.
Yeah, please.
Rotor field frequencies are NS. Yes, NS.
Not a rotor field, Baba. So the rotor field speed with respect to rotor. Okay.
Okay.
What is the frequency? What is the frequency of the stator currents?
So frequency of the stator current is F, sir.
F. You can see on the board, right? F.
Yes, sir. F.
Then what is the speed of the stator field with respect to stator?
NS.
NS. Then what is the frequency of the rotor currents?
Yes, F, sir.
And then what will be the speed of the rotor field? When F is giving NS, then SF will give how much?
Oh, yes, sir. SNS.
Understood, Baba?
Yes, sir. Understood, sir.
Right. Okay, Baba.
Thank you, sir.
Right. Alan Matthews from Kerala. Matthews.
Hello, sir. Am I audible?
Yeah, you are audible, Matthew.
Yes, sir. Sir, in the rotor field produced, the flux produced by the rotor field.
No. See,
uh,
rotor current, correct.
the flux produced by the rotor current will be in the opposite direction of the stator rotating magnetic field, no, sir?
No, it is in the same direction. Why? Because see, if I'm assuming this one as a rotor A, B, C, so the poles are rotating like this. So first the flux cutting will be maximum in A phase, then B phase, next C phase. Then what will be the phase sequence of EMF in the rotor conductor? ABC only. When it is ABC, the direction of the field is also ABC. It is not in opposite direction. Understood?
Yes, sir. Sir, but in that above diagram where we have derived that it will be dot, no, sir? The
See,
conductor.
it is the direction of induced EMF. It is not the field direction. So if you want to find out the direction of the field, you have to apply the direction of induced EMF, right? So you don't link those two things. Understood? You please just say when I'm giving a three-phase supply, then what will be the say if it is A, B, C, the stator conductors, stator winding,
Okay,
right? So when A, B, C, in which direction the field is rotating? Say clockwise.
Clockwise, okay.
Right. Then the flux cuttings in the rotor conductor will first A phase, then followed by B phase, then followed by C phase, right?
Yes,
Then
sir.
what is the phase sequence? A, B, C.
Yes, sir.
Then
Yes,
what?
sir. By imagining like this, I'm getting, but while
No, it
doing
is
the
the clear.
calculation, yes,
It
sir.
is the clear. It is the clear. It is the logic which you have to keep. Understood?
Okay, sir. Okay.
Understood?
Yes, sir. Yes, sir.
Right.
Thank you.
Right. Right. Yogasri.
కనెక్షన్స్ అనేటివి రాంగ్ అంటే రివర్స్ లో కనెక్ట్ చేసినప్పుడు యాంటీ క్లాక్ వైజ్ డైరెక్షన్ లో మూవ్ అవుతుంది సార్
Kadamma, it is not the question of wrong. The question is tomorrow in the interview they may ask if the phase sequence is ABC. Say the direction of the field is clockwise, the frequency of the rotor current is SF. For say, if I change the phase sequence, for say, why? Because this topic I'll be using in your breaking. For say, if I change the phase sequence, then what will be the frequency of the induced currents in the rotor at that instant? Appudu 2 minus S ani cheppali. Understood? It is, for example, if you are changing, then what is the answer? And you have to tell this. Yogasri. Understood? Hello?
సార్
Yeah, ma, please.
సార్ క్లాక్ వైజ్ డైరెక్షన్ లోనే రొటేట్ అవుతుంటది కదా సార్
Which one? Rotor is rotating clockwise direction. Understood? Right? But if I change the phase sequence at that instant, in which direction the field will be rotating?
యాంటీ క్లాక్ వైజ్
Then at that instant, due to inertia, in which direction the rotor will be rotating? For that instant,
ఆపోజిట్ డైరెక్షన్
that is clockwise direction. ముందు ఏదో ఉందో అదే డైరెక్షన్ లో ఉంటుంది. అవునా? See, is it possible for the rotor to rotate immediately in opposite direction?
నో సార్
Why?
సార్ ఇమీడియట్ గా ఎట్లా ఎట్లా చేంజ్ అవుతుంది సార్ కాదు
కాదు కదమ్మా. So due to inertia that will rotate in clockwise. Assume that initially the field is rotating clockwise direction. In which direction the rotor is rotating? Clockwise.
clockwise
Right. If I change the phase sequence of the field, that currents, in which direction the field will be rotating? Counterclockwise direction. Why? Because the field doesn't have an inertia. Immediately it will change. But due to inertia, in which direction the rotor will continue to rotate for that instant? Same clockwise, or it will change it to counterclockwise?
సేమ్ క్లాక్ వైజ్
Then this field is rotating in which direction?
కౌంటర్ క్లాక్ వైజ్
What is the relative speed at that instant? Ns plus Nr. Now, what is the frequency of the rotor current? 2 minus S into F. Is it clear, Yogashri?
ఓకే సార్
Right. Bhavani, already have clarified your doubt. I think you forgot to lower your hands. Lower your hand. Right. So no one is raising the hands. I'll stop for today. So still Manikanta. Yeah, Manikanta.
Sir, am I audible, sir?
Yeah, you are audible, Manikanta.
Sir, ఒక quick doubt, sir. మనకి relative velocity between stator field and rotor field should be zero కదా sir?
Obviously.
So అంటే లోడ్ వేసినప్పుడు ద బాడీ అంటే రోటర్ బాడీ ఇస్ డిక్రీజింగ్ ఇట్ స్పీడ్, అప్పుడు కూడా అట్లా మెయింటైన్ ఎట్లా చేస్తుంది సార్?
Yeah, when you are increasing the load, what happened to the speed of the rotor? Decreases.
Yes, sir.
Then the speed of the rotor decreases, the relative speed will
increase.
Then the frequency of the rotor currents will increase.
Yeah.
The speed is decreasing, but this field is increasing. The total will remain ns plus. The total will remain ns only. Understood?
Okay, sir. Got it.
Right? Okay, right.
Thank you, sir.
Right. Balakrishnan.
Hello, sir. Good evening, sir.
Yeah, good evening, Balakrishnan. Please.
Sir, my doubt is in line diagram, sir.
Yeah, you can see on the board the same
Sir,
line
in
diagram.
the final line, you put 2 times of ns. That how it comes, sir?
I never put 2 times. It is 5-2, Ray. It is not 2 times. It is 5-2. It is not 2. It is rotor field. It is not 5-2, Baba. Okay?
Okay, sir. Thank you, sir.
Right, Baba. Right. Purna Chandra Reddy.
Sir, am I audible, sir?
You are audible, Purna Chandra Reddy.
Sir, once explain if we load on rotor side, you said that EMF, the rotor EMF will increase and current will increase. Explain that condition, sir.
Whenever you are increasing the load, what happened to the speed?
Speed decreases, sir. Rotor.
When the rotor speed decreases, what happened to the relative speed between field and the rotor conductors?
Increases.
Flux cuttings?
Increases.
Rotor voltage?
Rotor voltage, EMF induced in rotor voltage will increase.
Current?
Current will increase.
Flux magnitude?
Will increase, sir.
Opposition to the main field?
It
will
increase.
Flux in the air gap?
Will decrease.
Then what happened to
Sir, my doubt is the main field flux and the rotor flux will be in same direction, no, sir? How will it happen?
See, maximum they will in opposite direction. That I'll draw tomorrow the phasor diagram. You can see they are not like exactly opposite. Mostly they are in opposite direction. Mostly. Then what happened to the flux in the air gap?
Decreases.
Then what happened to I1?
Increases.
Then what happened to power drawn?
Increases.
Then what happened to power fed to the rotor?
Increases.
Then obviously what happened to this torque?
Torque also increases. My doubt was that only, sir. That 5-2 and 5-1 are the opposite.
So if you want to just know as of now, so this is 5R.
Okay, sir.
So this is your rotor voltage.
Okay.
So this is your rotor current.
Yes,
right?
sir. Yes, sir.
So whenever you are increasing the load, this angle will increase.
Okay, sir.
So this is 5-2. So what is this component? This is 5-2 sine theta 2, right?
Okay, sir.
So when this angle is increasing, so this theta 2 will be approaching to 90 degrees. When theta 2 is approaching to 90 degrees, this component 5-2 sine theta 2, which is 180 degrees, is opposing main. Then what happened to flux in the air gap?
Decreases.
Then E1?
Decreases.
V minus E1?
V minus E1 increases.
Current drawn?
Increases.
Power drawn?
Increases. Torque increases.
Now it is clear, Baba?
Yes, sir. Yes, sir. Thank you, sir.
Right. Right. So Bhavani and Matthews I already explained to them. So I'll stop for today. So tomorrow we'll meet at the same time. Still, if you are having any doubts, you can contact me on number.